In this video, we want to solve all 6 problems of 2023 USAMO, United States of America Mathematical Olympiad, and I don't want to tell you only the answer. We want to analyze the problem, see related problems. At the end of, for example, most of the problems, I will leave some homework for you. You can solve them. That can be solved with the same idea. And we want to analyze the background idea for each problem. That, for example, the background idea that can be useful in many other problems in IMO, in BMO, British Mathematical Olympiad, and also other exams. Okay, and there are around 40-50 important formulas in geometry, combinatorics, algebra, and number theory. And if you want to learn them, as I said before in my previous videos, feel free to send message to my WhatsApp number in the description and comments. Okay, let's start. In an acute triangle ABC, let M be the midpoint of BC. Okay, the figure is this. Let's read. Let M be the midpoint of BC. Okay, and then let's do something. Let me erase from this board, and step by step we try to create this. Okay, so M is midpoint here, and then in next step it says what? Let P be the foot of the perpendicular from C to AM. So if I want to draw from C to AM, the angle here is what? Is 1 minus 90, 22. So it will be this point. So it is P. Now then, in next step, the problem says what? Let P be the foot of perpendicular from C to AM. Suppose that the circumcircle of triangle ABP. ABP. So let's draw a circle for ABP. Let's see. We should enlarge this. Should enlarge more. Okay, it passed through a little top, a little greater than this. So it will be from AB more. Let's consider AB a little smaller. APB. Okay, so this part and so on, tiny small. Okay, this figure is okay. Now we consider that it passed through A, B, and P. And it says, suppose this circumcircle intersects line BC at 2 distinct points B and Q. So this point is Q. Let N be the midpoint of AQ. Okay, so let's draw AQ. Let me draw it with red. And midpoint, so 156. It will be 50, 28, 78. So off of that, there will be some points like this one. So it is this, it is N. And now it says, let N be the midpoint of AQ, prove that N be equal N's. So in the problems, for example, also last problem of this year, we will solve like this. You can also a little focus on sentence of the problem. Here, if N be equal NC, it means that N lies on perpendicular bisector of BC. So because and one good thing here, one way you can draw CN NB and try to prove these two lengths are equal. One way to prove N lies on perpendicular bisector. And because N lies, we want to prove this. So we can say because M is midpoint of BC by assumption of the problem, it means that M is perpendicular to BC. We should prove this. Okay. Now let's draw this line. We want to prove NM is perpendicular to this. Now here it is 90. I try to find, can we find any cyclic quadrilateral? We will see it's not possible. But here we have something. let me tell you one important thing. We have 4 rules for cyclic quadrilateral. One rule is this. Let me show you. In problem number 6, in the beginning of the solution of problem number 6, I will analyze all 4 conditions. One of them is this. PA, ABCD. We know that PA, PD equal to PB, PC when ABCD is cyclic. This one times this one equal to this one times this. And here, because of this circle and M, can you tell me M what times M what equal M what times M what? MQ times MB, look, this times this equal to MP times MA, okay? MP times MA. Here, I want to focus on MPMA. If here it was 90, it was good because you said MPMA equal to MC squared, right? But let me tell you something. In right angle triangle, for example, it's this, it's this one, this one. We know that what? We know that it's so much famous. BH times BC equal to BA squared, right? What I want to tell you, so BH, for example, BHHC is AH squared, and the proof is by similar triangle. It's not hard, you can prove as homework. The proof. But I want to tell you exactly this idea, but in, as I said, for example, 40, 50 important formulas. One of them is this general form of this in any triangle. Okay, for example, we have A, we have B, we have C. Then, if we draw altitudes, this one. So if we consider D and consider E, and for example, let's consider, I think if we draw another altitude, it's better for this figure. It is E, it is H. Okay. Now here, you can say BD times BC. In these parts, A and E are on same point. So here, BD times BC equal BE times BA. And the proof is what? Because it is 90. It is 90. E and D are 90. They are equal to 90 and they see BC. They see AC. So because same angle, see one side, so we can say AEDC cyclic. AEDC cyclic. And then we can conclude that BD times BC equal to BE times BA. And let me tell you also another rule. This rule we don't need for this problem, but it's so much near to these things. Another rule in right angle triangle is BH times AC is AH squared. Here you can say BD times DC. Can you guess it is what? It is DH times DA. Try to prove these two things as homework. Again, this homework to prove. And also this one, all of them with similar triangles you can solve. And as you can see here, H also, let me call also this one D to have same name. Let me consider this one. It is, for example, D, BD times BC, BD times DC equal to AD squared. And as you can see here, H, orthocenter, AE are on same point. So when it will be, this part will be special case of this because BDDC, DHDA, here H and A are same point. Okay. So now that we know this part, let's go back to our problem. We have MPMA in this triangle. I said if it was 90, we could say MC squared. But if it is not, all of you know that if it is 90, it is this spot. When it is not cyclic quadrant, and when C is not 90, we can say, okay, MP times MA, we can also say it is equal to this times this. We can consider, for example, it's T, it is equal to MT times MC by the thing we said here. Let's consider this one, for example, lemma 1, the thing we proved here. So you can say by lemma 1, we have this because The reason was because APTC cycling. Now, if we consider first and last term, MQMB equal to MTMC. And by assumption of the problem, M is midpoint of BC, so MC equal to MB, and we can conclude MQ equal to MT, okay? So we can say this one equal this one, and because the whole part equal to whole part, this part also equal to this. Now, here we want to prove why it is 90, okay? We've not proved this yet, so let's erase this part. Now I want to use Thales theorem. Thales theorem, the problem says n is midpoint of A, so we can conclude by Thales theorem its application of similar triangles, or sometimes we can say it's for special case midpoint theorem. Nm equal to 80, and because nm equal to 80, it's 90. Let me tell you, Thales theorem is what? Thales theorem is this. Say Thales theorem. If you have two triangles, if you have, one triangle, for example, ABC, and we have DE, okay? BC, DE. Then, if DE is parallel to BC, you can conclude that in one way AD over AB, because the reason is triangle ADE will be similar to triangle ABC, because this angle equal this angle, then this angle equal this angle. By two angles, we can say these two triangles are similar. Then you can say AD over AB equal to AE over AC equal to DE over BC. Also, you can say AD over DB equal to AE over EC. And one important, and the reason is what? Because when we have this, by considering this part, you say because AD over AB equal to AE over AC, you can say so AD over AB minus AD equal to AE over AE minus AC. AC minus AE. You can do the same thing for this. As fraction, when we have x, y, z, t, then you can say x over y minus x equal to z over t minus z. And the proof is by cross multiply, these two things are equivalent. So you say AC minus AE, and AB minus AD is what? Is DB, so AD over DB equal to AE over AEC. Okay. So is this now also you can say if we have this, we can prove it is parallel. If we have this, we can prove it is parallel. The reason is what? If you have this, then you can say okay by ratio of these two sides, and because A is same, we can say if you have only two of them, it's okay. If you have, for example, only this over this equal this over this, because A is same by two sides and an angle between, you can prove it is parallel to this because angles are equal. Also, if you have this, you can use you can work with fractions and reach this part, and then you can prove it's parallel. So it is Thales theorem. By Thales theorem here, you say okay, Qn over Na equal to 1, and also Qm over Mt equal to 1, and then we can say by Thales theorem, Nm is parallel to AT. And because NM is parallel to AT, we know AT is perpendicular to BC because it was height. So we conclude NM is also parallel to BC. And we said if NM is parallel to BC, NM is perpendicular to BC, then we can say N lines are perpendicular bisector of BC, and NB equal to NC. Okay, this problem was related to cyclic quadrilaterals. Let me tell you a homework related to cyclic quadrilaterals from IMO. Let me open the file, geometry, this one. Okay, I think this problem is good. These are some ideas, and as I said before, if you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Okay, it is first one homework. I think is enough. If you wanted more homework, you can send message. Okay, let's solve second problem. And in this problem, look, we've used these two things, general form of this part. You know, all of you know this, but we don't pay attention most of the times to these two relationships. So the background idea is this, and it is only an application of this. The most important and most useful thing is to learn background ideas. You can solve any problem. Let's solve problem number 2 of USAMO, United States of America Mathematical Olympiad. It's for the year 2023. It's function problem. I released a video related to functions. There we have around 15 important formulas, ideas in functions, replacement. Consider a small example is f1 to 1. You should know those 15 ideas, and in any problem you can use IMO problems, USAMO, AME, AMC. So let's see what can we do here. It says let R plus positive real numbers be the set of positive real numbers here. Find all functions f from positive real numbers to positive real numbers such that for all xy in positive real numbers, f of xy plus f of x equal to x f of y plus 2. Okay. Here, we like to replace x or y or both of them with 0, but we cannot. Why? Because can only use r plus positive real numbers. So, let's start with x equal y equal to 0. Equal to 1, for example. If we replace, we can, let's consider, if you can't use 0, 1 is good. So, it will be f of 1 plus f of 1 equal to f of 1 plus 2. We reach this. Now let's only replace x with 1. It will be f of y plus f of 1 equal to f of y plus 2. Now let's replace y with 1. Then it will be f of x plus f of x equal to y is 1, x f of 1 plus 2. Okay, we've considered different cases. These two things are good. Here I can replace, because it is correct for all y, I can write it as f of x plus f of 1 equal to f of x plus 2. Now, we don't know f of 1 is what. From this part also we can't understand. So when you have, for example, you can write many things in terms of f of 1, and also if we had real numbers to real numbers and we could write in terms of f of 0, you can consider f of 0 is a constant c. Okay, here I define f of 1 equal to c, a constant c, and now I want to rewrite these two equations. The first one is this one, f of x plus c is f of x plus 2, and here f of x plus f of x equal to x c plus 2. Okay, now I want to write because x plus c, this one I want to write an equation that combine these two things. How? I say, okay, let's consider, for example, x plus f of x plus c. If we have this, let me consider this is first equation, second equation. If we use first equation here, then we can say what? It is this part plus c. So in first equation, x something plus c is what? F of that thing plus 2. So f of this thing, f of x plus f of x plus 2. And f of x plus f of x, we can use this. Second equation. It will be what? It will be xc plus 2 plus 2. So it's good. We found xc plus 4. And now let's pay attention to the main equation here, f of xy plus f of x equal x f of y plus 2. Let's copy and paste it here. I want to pay attention to, let me write with other color. Pay attention to this part and this part. I say, okay, f of x, x plus c, I want to be equal to xy. So if x plus c equal to xy, so it means that if you divide by x, it will be 1 plus c over x equal to 1. So if I replace x and y with this, so f of xy will be x plus c plus f of x. So main equation, we call main equation star, and we call this equation 3. And let's move it, because we want to count it in two ways. If we use the star, it will be what? X y is what? 1 over plus c over x plus 2. And here, if we apply third equation we've reached, it is xc plus 4. And that's good because we found f of something equal to this. Okay. Now, let's rewrite it. F of x, f of 1 plus c over x plus 2 equal to xc plus 4. At first, we subtract both sides by 2, so xf of 1 plus c over x equal to xc plus 2. And in next step, I divide both sides by x, and we can divide because the problem says x and y are positive real numbers. It is not 0. It will be c plus 2 over x. Now, here I say, okay, if we want to find f of x is what? I say, suppose we know y is 1 plus c over x. So f of y equal to c plus 2 over x. X is what in terms of y from this equation? Look, we know 1 plus c over x is what is y. So I want to find x in terms of y because I want to replace here. Or I want to find 2 over x. So c over x is y minus 1 if we subtract by 2. If we divide by c, 1 over x is y over c minus 1 over c. Okay, now we multiply by 2, 2 times y over c minus 1 over c. Okay, so we found this, and I can replace x with y. Both of them are okay. I say f of x equal to c plus 2x over c minus 2 over c. Okay, so c plus 2x over c minus 2 over c. Now I want to use it, and I want to replace with in main equation. So let's consider this. Okay, let's replace this part. I want to see c should be what? Do we have any answer? So at first I replace here f of xy plus f of x is c plus. Let's consider constant term first. C minus 2 over c plus 2x over c. So I write c minus 2 over c plus 2x over c equal to x. Again, f of y is what? Is c minus 2 over c plus 2y over c plus 2. The next step, I want to find f of this step. You write again c minus 2c plus 2 times this part over c. So it will be c minus 2c plus 2 times this part, 2 times xy plus c minus 2 over c plus 2x over c over what? Over c. I replace this one. Equal to x c minus 2 over c plus 2y over c plus 2. Okay, now it's good because we don't have f. Now in next step, if we consider, we should multiply by c and again c because we have two c's here. So let's multiply by c squared. The first one will be c cubed. The next one will be negative 2c squared. This one, we have c here. So when you multiply 1c will be cancelled. It will be 2xyc because we multiply by c squared. This one, c over c is 1. So it will be 2c squared. This one, c 1 over negative 2 over c squared will be cancelled. It will be negative 2 times 2, negative 4. Again, c squared will be cancelled. 2 times 2x, 4x. Now, if you multiply by c squared, it will be c cubed x. We multiply by c squared minus 2cx. We multiply by c squared 2xyc plus 2c squared. Okay? Okay, let's cancel the things that we have on both sides. 2xyc, 2xyc. Negative 2cx, we don't have 2c squared on. 2c squared, we can cancel. Now, here, let's rewrite the things that are left. It's c cubed minus 2c squared minus 4 plus 4x equal to c cubed x minus 2cx. So as you can see, these terms are good related to each other. and 2c c minus x. And sorry, because we have negative 2 over c here, we should write negative 2c, okay? We have this term, and okay, so here, if we take these to right side, c cubed x minus c cubed, then plus these two terms are similar. You can factor from negative 2, you can say negative 2cx, let's write like this, plus negative 2cx minus 2c, if you take it to right side, will be, okay, we write negative 2cx, and we take it to right side, negative 2c will be 2c, plus we take this to right side, it will be 4 minus 4x equal to 0. Here we reach, okay. Now we consider c cubed here, x minus y, we factor here from negative 2c, it will be x again minus 1, and we factor from negative 4, let's write negative 4, x minus 1. Then here we factor from x minus 1, we write it as c cubed minus 2c minus 4 equal to 0. We know it is correct for all x's that are positive real numbers. For example, you can consider x equal to 2 or anything. This part is not 0. So we conclude c cubed minus 2c minus 4 equal to 0. We want to find all answers for c that are positive real numbers, because f of 1 is c, and c should belongs to, by assumption of the problem, to positive real numbers. Here, because the degree is 3, I told in my previous videos, one important thing is to find at least one root. If you check C1, 1 minus 2 minus 4 is not 0. If you check C2, it will be 2 cubed 8 minus 4 minus 4 0. So because C2 works, we can factorize, and one factor is C minus 2. And then we place C squared, it is C cubed minus 2C squared plus 2C squared. Then plus 1, let's see, because we have negative 4c, we should add 2 plus 2c minus 4 equal to 0. So this part is 0, or this part is 0. If this part is 0, then c equal to 2. One answer is this. If this part is 0, it's not possible, because look, c squared plus 2c plus 1, we can write it as c plus 1 squared plus 1 equal to 0. Because we know that famous identity that a plus b whole squared is a squared plus b squared plus 2ab. So c squared plus 2c plus 1 is c plus 1 whole squared plus 1. And we know this part is at least 0, so this part is positive, is at least 1. And that's a contradiction. Or you can also use quadratic formula. You can say delta or discriminant here is negative. We don't have any real solution. So c is 2. Now, if we replace c with 2, it works. So f of x, c is 2. 2 minus 2 over 2 plus 2x over 2. 2 minus 1 is 1. 2x over 2 is x, x plus 1. So f of x equal to x plus 1 for all x. In positive real numbers, we proved f of x equal to x plus 1. And because we replace here, we don't need to replace it anymore. But always one thing, because maybe we have careless mistake, at the end also check it again. I say f of x is x plus 1. Now this part is xy plus x plus 1 plus 1. I want to see, is it equal to x times y plus 1 plus 2. Then right side is xy plus x plus 2. We can cancel xy, we can cancel x, and 2 equal to 2, and we see it works. So our solution for this problem is this. Let me write some important rules in functions. You should consider special cases. Special cases means, for example, x equal to y, x equal to negative y, and so on. Consider small example like in this example, in this problem. For example, x equal to 0, y equal to 0, x equal to 1, plus, minus 1, and so on. One thing is f1 to 1. It is also useful. For example, in PMO for Philippine Mathematical Olympiad 2023, it was useful. In IMO, useful. IMO, PMO, and so on. Sometimes we have a complicated term, for example, f of x, for example, plus f of x plus f of x, for example, equal to something, equal, for example, f of x plus f of y and something else. You should do something, and you should write two equations to get rid of that complicated term, okay? For example, you don't change x, you only change y, and you get rid of complicated term. Another one you can say is f surjective or not. Analyze f of negative x, and so on. As I said, there are around 15 important formulas, and with each of them we can solve IMO. We should solve around 6, 7, 8 problems of IMO related to functions, and then you can solve any other function problems. They are similar and good. Related a little to combinator is the thing you should replace, you should think. We can say somehow it's combination of combinatorics and algebra, especially when you work with f of, for example, positive integers to integers, you can create cycles, something like this. We have also graph permutation or permutation graph. Okay, if you want to learn ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. And please don't forget to subscribe. Turn on the bell and like the video to have next videos. Okay, thanks. See you next time. Now let's solve question number 3 of 2023 USAMO. We had similar problem, an easier problem in USAJMO 2023. Here we should find all possible. In USAJMO, we should find only maximum instead of all possible. Okay. So it is general case of that problem. If we solve that problem, I released the video, the solutions of USAJMO. Now we want to work on this problem and see what are the other things that we should prove. Okay, let's read the problem. Consider an n by n board of unit squares for some odd positive integer. So n is odd and it's important. We say that a collection C of identical dominoes is a maximal grid aligned configuration on the board if C consists of n squared minus 1 over 2 dominoes where each domino covers exactly 2 neighboring squares and the dominoes don't overlap. So let me tell you, we have n squared cells, but it is odd. We can't cover all of them with dominoes. One cell will be left. So we can cover n squared minus 1, the number of cells at most that we can cover. Now if we divide by 2, because each domino covers 2 cells, so the number of dominoes will be this. That's the reason it says maximal, because you can't place any other dominoes because one cell is left. And here it says C then covers all but one square on the board. We are allowed, so let me draw one figure. Okay, let me show you, for example, one example is like this. This one, for example, it is another domino, and one cell is left. Look here, how many cells are there? 3 squared. How many dominoes are there? Minus 1 over 2, which is 4. 4 dominoes. And then it says, okay, covers all but one square. We are allowed to slide but not rotate a domino on the board to cover the uncovered square, resulting in a new maximal grid aligned configuration with another square uncovered. Like this, you can slide this one to up, and then it will be what? It goes to here. So then we can erase this. Now the uncovered cell is here, okay? Again, you can also move this one, and it says what? It says let K of C be the number of distinct maximal grid aligned configurations obtainable from C by repeatedly sliding dominoes. So again, you can move this one to right. So we have another configuration. Let's erase. Now for this board, we can't create any new configuration. Okay, it says find all possible values of K of C as a function of F. Also for the case maximum, I've tried to use a small example also for this one that is all possible. I use a small example. So I can say one of the most useful idea is considering small example is useful in many problems of we can solve many problems of IMO with this idea. And after solving this problem, I will leave some problems as homework to try them. So let's consider with n3 because it says n is odd. N1, look, we have only one configuration. Okay, now let's consider n3. So if I consider n3, I want to consider, let's consider for example one case. One case is it is empty, this cell. And then let's consider it is this one. And in this case, let's consider these two point to this one. And these two things, for example, let's consider only this part. Let's analyze this part first. So we can say that you can move it to, let me tell you, we can move this one here or the other case because we should find all possible cases that are obtainable. If, let me copy from this part. Okay. Now in this case, I want to move this to up. So erase this one. Then I can move this one to here. So let's copy this case. And we move this to left. Okay. Now as you can see, in this case, we have 4. Okay. So 4 is possible. Let's consider another case. If I want to consider another case, at first let me also tell you something. If we color the cells with black and white, it is I can say it is for all ends that are odd. Look, if you consider the corners black, the number of black minus the number of white is 1. And the proof is so much easy. Because you say, okay, in this part we have, it is even, and in each column we have equal number of black and whites, and in this part also we have equal, one cell is left. So number of black minus number of white is 1 in all odd by odd. And because each domino covers exactly one black, one white always, so one black will be left. So the cell, the whole cell that is not covered is always black. Okay. Now we've considered this cell is empty, but the configuration was this. Now, if I want to consider, for example, let me tell you another cases, for example, that this cell is not covered, I say, okay, in this case, 2 are point like this. So if I consider again 2 point to this, 2 dominoes point to this cell, I consider here vertical, horizontal. Now I consider vertical. Now if you consider from this point, if you consider it is same as this one. So again, for this one we have 4. Let's consider the case that this cell we don't have like this, and it is not pointing to this, so it is like this. So in this case, we know that it has to be like this, and it has to be like this, and it has to be like this. So let's see, have we calculated this case? If you pay attention, this case is, let me see here, also it's exactly similar to this one. Look, because when we have this as whole, so look, these two similar to these two, this one similar to this one, and this one similar to this one. Okay, so again, it will reach 4. And so if the hole is on the corners, it will be like that. Now, if it is not like this, it is, for example, the hole is in the midpoint. Okay, if the hole is in the midpoint, let me consider this here, is the mid cell. Okay, if the hole is here, look, this one is covered by this or left, and both of them are similar. Then this one, then this one, then this. Okay, now in this case it reaches 1. So Here we found for 3 by 3 the answer is 1 and 4. So for n1 the answer was 1. For n3 the answer is 1 and 4. Now let's check n5. After n5 we work on general n. Okay. So for n5, now let's consider the black cells. Sorry. Here, let me tell you something. I want to consider the holes. Okay. I want to see at first, can I create one? So if I want to create one, if I consider this one, then for this one I have problems. So I try to focus again on this part. Then as you can see, we have this, and the rest you can cover like this. And then it cannot reach to any other cases. We could create one again. Now let's see, can we create two? Let's copy this one. Okay. Okay, for this one, I want to have two holes. Let me tell you, the holes are like what? This hole and this hole. And I want to only be able to reach from one of them to the other one. So if I have this one, then it moves to this part. Then I don't want to move like this, so it will be like this. This one will be like that, like that, like that. This one, and then we have this. So as you can see, we can only slide this domino and we can reach two cases. So 2 was possible also. Let's check, can we create 3? For 3, let's consider this one, and this one. Look on. How I understand quickly this example, because I solved this before. So in, for example, one step, we can't reach these 3 cells. If you check some of them, you will understand, okay, this one is good. And we have 2 layers, outer layer, inner layer, for example, this one, and I will explain this. And for example, I've checked first on this level, I couldn't find any 3. Then I tried this one. So let's see. If we consider this one, then we can consider these two things. And then here, for here, I consider this one. And then for this part, I consider this one. Let's see. This part, this. Okay, so you can only slide this one to right, this one to up. So then we have 3 cases. One case is here, one case after sliding this one case after sliding this one. Now let's consider 4. In 4, I consider this one, this hole, this one, and this one. And I consider, let's consider like this one, and I think, okay, if you consider like this, I think it's not good. So, so I think when we slide this, it is at first empty, then it is empty, empty, 3 plus 1, 4, it's okay. We should draw other dominoes such that they shouldn't point on these empties, on these 4 cells. So for example, look, this, and it's not, if you draw, it will be good. So look, it will be this, for example, this one. So 4 was possible. Now, if you want to, let me tell you something. If we want to, for example, create 5 or something else, when we consider these 4, we saw that we can't have any other more. Let's draw something that is larger than 4. You say, suppose it is empty. Then you say, okay, we consider this. Let's, what happened? Okay. Let's consider cells like this. Okay. And then it will be empty. Then this one. Okay. And then other dominoes. So we can move these things like this. And in each move, we can create one more configuration. And the others are like this. So how many cases are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 plus first case, because we can have 8 moves plus first initial case, 9. So we could create 1, 2, 3, 4, 9. And now look, if you check, for example, I've checked 5, 6, 7, 8, 9. For example, let's check one of them. Let's see, for example, can we consider this one? And then, for example, 1 step, 2 step, 3 steps plus 1, 4, 5 steps. Then it is empty. I don't want to use this. So I say, okay, I create this because then this one will be empty. Look, this one will be empty, this one empty, this one empty. Then I draw this. Then because this one is empty again, I want to draw this. And because this one is empty, I draw this one, this one, this one, this one, this one, this one. Let's see what happens here. You can move this one when to left. Then when you move this one, then you can move this one, then you can move this one. So if we want to, one problem here is this: it can goes to here, it can goes to here, and this can goes to here. So how many choices are there? 1, 2, 3, 4, 5, 6, 7. Let's see. Do we have other cases? It can be empty, it can be empty, it can be empty, it can be empty also. When we move, it can be empty. And we can also move this one. So 1, 2, 3, 4, 5, 6, 7, 8. And initial case 9. Again, it will be 9. And if you want to create 5 to 8, it is not possible. You will see all of them reaches to 9. So we guess what? We guess that for n, our answers are what? We know n is even, n is odd, so it is 2k plus 1. So as you can see, it's 1, 2 to what squared? For here, it is 2 squared, 1 to 2 squared, and 3 squared. For here, it is 1 squared, and last word 2 squared, 1 squared. So 2 is what? Here we add by 2 here, 2, 1 squared goes to 2 squared, add by 1. So 5 plus 5 minus 1 over 2 is for this. So this 1 minus 1 is k. It will be 1, 2, 3 to k squared. And the last one is k plus 1 squared. So our claim is that we can create only these things. All of them are possible. And except these things, it's not possible. So let's first prove that these things are possible. Then we want to say other numbers are not possible. Okay. For proving this part, I want to say n7. For n7, the cases are what? So let's focus on that first. Okay, and also I will prove that if the whole is determined, then the configuration will also be determined. I will prove after creating these things. So for n7, k is what? It's 2k plus 1, 7. So k is 3. And I want to prove I can create 1, 2, 3 squared and 4 squareds. I want to prove that I can create 1, 2, 3, 4, 5, 6, 7, 8, 9, and 16. Okay, so for 16, we have a famous configuration, or let's say famous, a spiral. If we draw a spiral, and the whole is like this, like exactly previous part for n5, what we've done like this. We say, okay, if we draw like this, if we draw like this, if we draw like this. After considering 7, we generalize for 2k plus 1. We consider this one, this one, this one, this one, then this one, and this one. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we could create 16, and the rest, look, you can place like this. Okay, now I want to prove 1 to 9, how we can create. I try to find a pattern to prove all of them because there are 9 cases, and in general, we have k squared cases. This one, 16 or k plus 1 squared, is similar to this spiral configuration. Let's consider 1 to k squared. To k squared, or here 1 to 3 to 9. Now let's use this table again. Okay, let's erase this part. Let me tell you, for example, how you can create, for example, 5. Okay. You consider this cell and you say, okay, 1, 2, 3, 4, 5. Then you block this one. Okay. And let's see what happens. So let's draw the other things by. So you block by this. Let's show the other one by green. Because only blue dominoes should move. 1, 2, 3, 4. 1, 2, 3, 4, 5. 5. I'm creating 6. Let me tell you this one. Okay, and if I want to consider with green, I can say let's move them like this one. And because I don't want to mention this part, I think I can like the example for 5 by 5 when I wanted to create 1 to 3. I've used this layer, okay, not the outer layer. So here also, let's use that. So I erase this part. I want to create 6. So I consider this cell, then I say, okay, 1, 2, 3, 4, 5. And because 5 movements and initial case is 6. Then I block this with red one and then I draw the rest by green. Okay, it will be this, this one, this one, this one, this one, this, and the rest like this. Okay. And because the empty cells are this one, this one, this one, this one, this one, this one, as you can see, we don't have any other dominoes point to these things. And for example, let me tell you, in general case, it was for 6. Let me open new page. So if I want to create, for example, 9, I say, okay, this one, 1, 2, 3, then 4, 5, 6, 7, 8, okay? And then I block this one, and then I fill the rest by green. Look at this one, this one, this one, this. It will be unique, okay? For example, if I want to create 8, I say this one, and then 1, 2, 3, 4, 5, 6, 7, and this one I block this. Then with green I create this one, and then I can consider this, and I fill the rest I fill the rest with green dominoes like this. I start from here, and it will be unique. So look, we should focus on what? On these dominoes. And after each part I wanted to block, I do this. So here I've created what? 1, 2, 3, 4, 5, 6, 7. And with the initial case 8. Let's, for example, case also small cases like 1, 2. So if it is 1, here you should block. Okay, and then the green one will be like this, and the rest you can fill. For example, if you wanted 2, you say, okay, I select this one, then I have only one domino, then I block this, and then I can fill like this one, this one, this one, this one, this one, and this one will be this. So it is 2. For example for 3 will be what? If, let me draw with blue. So this one, it was example for 1, it was example for 2. Let's consider example for 3. For 3, when we have this, you block like what? You block here. And then we fill like this, and it will be finished. And the rest with dominoes is 3, And because 4 is a little different, we have like this, we want to see how we can block 4. So we want to reach 4. You consider this cell, you consider this one, and 1, 2, 3, and it wants to go here. So here, if we had, for example, 5 or something, we draw this to point to this, but we block this point like this. This. Okay, and the cells that can be empty are these. Now, if we fill like this one, and then we fill like this, okay, it will be like, this one will be bad, let me tell you. First, we should draw around that. Let me erase this part. Should block like this. Let's do something. I want to find a pattern that works. Let's erase this. Let's erase this. Let's erase this. And let's say, for example, always we consider this red, so these red dominoes like this, and then let's consider some other thing. I think it's better. Let me erase more. Erase more. We consider this. Let's consider, for example, let's block this part, this part, this part, or let's do something. Let's consider this blue hole here. Let's consider it is always like this. And, or let me consider other part. This one, this one, this one, or this, this one, this one, this. And in general, for blues, I have this. Let's consider this one, this one, this one, this one, this one. And some of them will be what? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is for 9. And in this case, let's consider the red parts will be like what? Will be like this, and this part, this part, this part, this part, this part, this part. So this answer is for 9. And now I want to say from this example how I can create 8, 7, and other answers. So it is 9. Let me paste another figure to not miss this figure and change it. So for 9, I've created that. For 8, I want to change this. Okay? For 8, let me tell you I do what. I consider this red. And I erase. Let me delete this. Let me delete this. Then I say, okay. I consider this part. I block this. Then I place also this. So the empty cells are what? Let me draw with blue. This one. 1, 2, 3, 4. 6, 7, 8. And look, no dominoes point to this except the blue dominoes point to these holes. Okay. Now let's consider, if you want to consider, so 8 was created by 9. Now let's again use 9 to see how we can create 7. For 7, I should block from this part. So I should remove this. Let me consider this one. So our holes will be on these points. And I should block here. So we shouldn't point to this one. It will be like this. And then I will consider, let's see. For this part, let me tell you, I also erase this one. And I select this one. I select this one. I select this one. And now it will be okay. Okay. For 7, I've created like this. Let's consider for 7, I wanted 1, 2, 3, 4. 1, 2, dominant 3, 4, 5, 6, and 7. For initial case, now I want to create 6. So 1, 2, 3, 4, 5. up to here. I should remove all these parts. Okay, so let me remove these parts. So the holes will be like what in this position? 1, 2, 3, 4, 5, 6. Now here we don't have this part and we should block here. And here again we should use borders, okay? Means I use this part, I use this part, I use this part, I use this part. Now I blocked. Okay, and now it will be okay. It was 6. Now let's see how can I create 5. So in this position, when I want to create 5, I say 1, 2, 3, 4, 5. So I should block. This part is easier part when it is in the middle of the direction. You select these two things. Okay. And also you select one in the border. And then we say what? We say okay. We have, let me draw with red. We have this part, this part, this part we blocked. But now we found this, for example, what was that 6, 5, and we can do like this. Now we want to generalize, okay? We want to generalize for 2k plus 1, which is an general odd number. How I can create 1, 2 to k squared like this, and how I can create k plus 1 squared. Okay, let's prove it. We found the idea approximately, and now we can apply it for general 2k plus 1. Okay, now let's see our example here. It was blue. So we select, for example, this cell is empty cell. At first, let's create k plus 1 squared. Okay, it's easier. You consider this whole, and you say, okay, let's consider this part, this part, this part, and so on. Look, for example, let me tell you, it is 1, it is 2, it is 3, it is 4, it is 5. It is 2k plus 1, it is 2k. So because it starts with even odd, the last one will be like that. Then we start from even odd again. Even odd because it will be 2k plus 1. Then we start with even odd again, 2k minus 1. Even odd, so it will be even odd, then it is 2k. Again, even odd, 3, 4. 4, 3, it will be like this. And then you say, okay, holes will be this part, we'll move to this part, to 5, then to 2k plus 1, then to 3, then again to this part, then again to this part, again to this part, again to this odd one, this odd one, these 3, and then if we consider this 1, then whole will move to this part, okay? And now, let me tell you, we should use induction for this part. If we consider this part, again, we use same thing for this part. It is n minus 4 because the whole part is n. 2 rows from top and 2 rows from bottom were removed. So it will be n minus 4, n minus 4. And in n minus 4 is 2k plus 1 minus 4, which is 2k minus 3, which you can say it is 2 times 2k minus 4 plus 1, which is 2 times k minus 2 plus 1. Now, in the green part, we know we can create for this k plus 1 squared. For this one, we can create k minus 1 squared. We have cases here. Now, how many cases are there in this part? You say, okay, you move this one, this one, this one. How many are there? K. And then you move this one, this one. So you have k movements, and on one initial case, you have also one initial case plus k and plus k here. Then plus k movements here. This one plus k minus 1. We don't consider this movement because we've counted it here. It is in the green box. So if we add these things, it will be k squared minus 2k plus 1 plus 1 plus k 3k minus 1. It will be cancelled, negative 2k plus 3k. Let me calculate. I forgot this part. Look, it is k. It is k. Also, it is k. So we have one more k. And then this part is k minus 1. So it will be plus 4k. Plus 4k, it will be k squared plus 4k minus 2k plus 2k plus 1, which is k plus 1 squared. So we could create this one by induction, and we've used n minus 4 to n. By induction, your base case can be, for example, 3 and 5. 3 and 5 are okay, because by 3 you can create 7, by 5, 9, and so on. And we proved in base case 3 and 5, I said, let me tell you, for 3 and 5, for 5, I told you how to create 9 here. Also for 3, we worked on that, and it was, example for 4 was this, okay? Now, let's consider, so we proved that we can create 2k plus 1 wholes, 2k plus 1, k plus 1 squared, and we can prove that let me tell you, the other things here should be like this one, this one, this one, and look, because 1 is left here, you can say 2 is left, and when you draw, it will be like this, it will be like this, and it will be like 1 whole. I'm sorry, we should start from here. I want to block green part from rest of the figure, so it will be like this, and you can continue like this. In general, it will be like that. Okay, so we can see there is no, except only this part, we don't have any connection between blue parts and green parts, so it cannot be, it's k plus 1 squared, and we don't have any other part, and let me tell you something. So the blue parts are unique like this, you should only move, and then after that you can use by induction. Also in green part we have something like this unique. Now, so for this example, I've created k plus 1 squared, and also I will prove why it is not possible to create more than that. Now let's focus on how we can create 1 to k squared. Now I want to create, like, let me tell you, like this part, that we had some blues. So we can use this layer. We want to focus on 1, 2 to k squared. So we consider this part, this part, this part, this part, this. It goes like this one, this one, this one. Okay, so as you can see, we want to see how many movements are there if we consider all of them. So you say in second row, how many? We have one initial configuration. So in this case, is 1, 2, 2, 2k plus 1. Now we can consider what? We say, okay, 2 from here, 1 from here, 3 2k plus 1 minus 3. In each row, we want to see how many shapes are there. It will be 2k plus 1 minus 3 over 2 shapes. And how many rows are there? Second row, fourth row to 2kth row. It will be 2k over 2. So we have this number of rows, and in each row, we have 2k plus 1 minus 3 over 2 plus. Now these cases. First one is 2 to 3. The next one is 4 to 5. So we consider 2 to 3, 4. Let's consider, this is 3 to 4. Then 5 to 6. Okay. And the last one is 2k minus 1, 2k, 2k plus. So from 3 it starts, the last one 2k minus 1, 2k minus 1 minus 3 over 2 plus 1. Okay, so it will be 1 plus 2k minus 2 over 2k minus 1 and times k plus 2k minus 4, which is k minus 2 plus 1. Now it will be what? 1 plus k squared minus k plus k minus 2 plus 1. So you cancel this, negative 2, 1, 1, it will be k squared. So if we consider all of them, it will be k squared. Now let's consider red parts. Now, like our small example, we consider this part, this, and here we consider this red, red, and we feel all of them, all others will be unique now, if you want to consider all of them like that. Let me tell you one thing first. Okay, we start from this part. Okay, it will be like this. We start from this part. We consider this part. Like that. We consider this part. And last part like this. Okay. Now suppose, for example, our answer, it says 1, 2, 3, 4, 5, 6, 7, 8. It goes up to this part. We want to finish. We want that it be the last part that we want to create. So let me copy and paste. We change it to what? We want to find general form of this. So in this case, when it is last part, we should remove this. It shouldn't point to this part. And we want to block this. Okay, so you block this part. So our blue cells will be what? Will be this part, this part, this part, this part, this part, this, this, this one, this one, this one, this one, this. Now we blocked here. Let me tell you something. Always we consider this red and this red. We don't want to change them. Let me maximize it. We consider this one and we consider this one. Okay. And let me tell you, it's better to let's consider this part. This part and this part. We don't change them. And it is from left to right. Look, we should consider the options. Here it's go to right, go to left, go to right. When it is go to right, when it goes to right, let me tell you something. Here we block this part and we can consider the rest. And let me tell you something. Because the border of this is important, so we should remove, let me tell you, we should remove this part. Let me write the rest that changing green this part, and then I will remove these things. Then I should select this one, and then I consider the border again. So let me erase this part. Let me erase this part, border. I want to disconnect this part. Okay. So when I consider this, I write like this to block that part. Okay, I blocked this part now. The rest will be like this and it will be okay. Okay, understood? So it was what? It was when it goes right, left, right. Now we want to consider if we have, for example, it goes to left. So let's copy this part. Control C. So it goes to right and we blocked. Now in the next case, we want to consider, for example, it goes to left and we block, for example, right, left. For example, up to this part, we want to consider the last part that we have is this. Okay, so here when we consider this part, we remove this, and I block here. Okay, now the empty cells can be in what points? On this point, this point, this point, this point, this point, this point, this one, this one, this one, this one, this. Now again, I use same strategy. I erase this part. I use green ones, and then here the border is okay. We don't want to change the rest. So I blocked. So when it goes from left to right, right to left, we've considered. When it is from left to right, we've considered. Now, if it is on these parts, okay, we should consider also the borders. Suppose, for example, we want to consider up to, let me erase this part, up to this one. Okay, here it will be stopped. Now, I say, okay, we have this one, this one, this one, this one. Let's consider the empty cells. This one, this one, this one. Okay, up to this part. This part now I should block here. I say okay. I block with red domino. Now in this part, I erase these parts, and like previous one, I also erase this, I also erase this. So we have what? We have this one, this one, this one, this one, this one. Now, because we've occupied two cells from the border, from this border, I mean, you can tile it again. You can erase the rest, and you can tile it. Erase only red tiles here, and it will be okay. Okay? So let me show you here how you can do that. The green part, you consider this one, and this one. So we've considered this from left to right, from right to left, and only one case is left. If we want to consider, for example, from here, the first one from left, or for example, if it goes from right to left, the first one from right. Let's consider also those cases. Suppose that, for example, we consider up to this here, and we want to block from here. So we should again block this one. So how can I block this? I erase these two things. And how I blocked? Okay. And I will block from here. Here. Let me draw with green here. This part, and then I consider, because two cells are removed from border, so we can cover with green the rest, like previous time. And the last part that is left, it was first from right, first from left. And most of them are similar. I just want to show you that with rigorous proof, if you can't understand, for example, why they are similar. So in this part again, when I want this, I try to block this part. I select these two things, and then I consider this one, and the rest is same. You don't need to change the border. Okay, so we proved by these things the number of holes here we can create from 1 to k squared. Now I want to prove why except those numbers we can't create anything. Okay, let's write all the things that we can create. N is 2k plus 1. We proved 1 to k squared is okay, all of them. And k plus 1 squared also is okay. Why the rest are not okay. Now, the first thing I want to prove, we can consider lemma 1. If the whole is determined, then and it is reachable. If the hole is determined, for example, we've reached this case, the hole is here. We've reached also other case, the hole is here. And from, for example, first case A, you reach, first case, for example, C, problem says we reach to A and reach to B. If the hole is determined, then we can say A equal to B. We prove it by contradiction, suppose A is not B. Okay. Now let's consider, let's copy a figure, for example, of 7 by 7. 7 is okay. So now, suppose, let me tell you something. If, let me answer this. No, it's okay. When you reach A, you, for example, do some, for example, some operations, the movements that you can do, slide the dominoes, and for example, you reach B. Look, you can also reach from A to B, because if you slide, for example, this to right, if you do to left, then it will be bilateral, and we can reach from A to C. Also, you can reach from B to C. So, if, for example, suppose it is A, you can reach from A to B. Okay? Now we know the holes, for example, both holes are here and here. Okay? Without loss of geometry, suppose the holes are here. Now, some of you have dot, 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 means it is not only 7 by 7. It's for general 2k plus 1 by 2k plus 1. Now in next step, we know that, for example, when we wanted to move from A to another case, for example, A to X, we had this cell, this empty cell, and without loss of geometry, we had one domino here, and we moved to this part. Okay, and now the hole will be here. So, suppose B is the first time that we see this hole. Okay, so if B is not that, consider another one. Okay, so suppose, for example, we consider B prime. B prime is when you want to reach from A to B. B prime is the first configuration with same hole as A and B. So we don't have any case between them that this is our hole. Now, if we consider, I think we should do something. I should minimize it. Or let's do something else. Let me select complete part. Okay, and this part with the same hole. And this is our B prime. And this is the case before that. Okay. Now, for example, it is A, it is D, it is E. Because it is the first time that we have again this hole, so we know here we didn't have we've not moved this one. Why? Because look, if we want to move this one, you can't move it here. Why? Because the hole can only be on this part, or this part, on black parts. Look, if you consider, I said in the beginning of the solution, on black parts. If you want to move this one, you can only move it to back, to left. If you move it to right, then what happens? This will be the whole cell, but the color of this is white if you consider the color is black. So we cannot move this one until this step. So we move this one to this one, and now we understand something. In E, we had this part, so because we could move this to left, the hole was here. Now, as you can see in D and E, the hole is in the same cell. So if in the beginning of the solution, I say, for example, consider the distance from A to B prime, the number of steps that we can reach. If you consider D and AB is minimum between the cases that the holes are in same cell and A is not B, If you consider DAB is minimum, so because D and E have same hole, we know that the distance of D and E equal to distance of A and B minus 2 because of these two steps. So we conclude what D is equal to E. Okay? Because if D is not E, then we have contradiction because in the beginning of the solution you should define this. I wanted to say you the beginning of this solution of this lemma, but maybe you said how can we understand? We understand exactly here that we find another case inside it. So you say we consider the minimum one. So D equal E. When D equal E, it means what? Let's consider. It is this. Then it is B prime. Okay. So as you can see, here you moved it to right, you moved it to left. So A equal to B prime. But here I said consider, I don't want to reach A. We can say without lots of generality, we can consider A. Between A and B, we don't have any A again because if you have A again, you consider this. So you consider the minimum distance between A and B, and then we said, okay, if B prime has same cell, we consider this one, and we've considered what? We considered A and B has the minimum distance between all cases that have same hole. We don't have A here, and we don't have any other cases, so we can say that. We don't have also B prime because we said it has the minimum distance, so this one should be B. If we consider this minimum, then between A and B, we proved what? We have only one more case because if the distance, if D is not equal to E, these two things have same hole and the distance is less than D and A and B. So we have this and we said it is B, so we proved A is B. Okay? Proof was this. If you had question about the proof or because I don't know your question is in what part, I try to explain as much as I can. If you had any question about this, the proof of each part, feel free to send message to my WhatsApp number in the description comments. Okay, so we proved lemma 1. Now I want to prove that the maximum is k plus 1 squared. Why? This part is important. Lemma 2. Kc is at most k plus 1 whole squared. Then we want to prove our only good numbers are these. So we want to reject after k plus 1 whole squared. Then we should reject between k squared and k plus 1 squared. So k of c is at most k plus 1 squared. Let's consider. Let's go to the problem. Let's copy one figure, for example, that has more cells. I think this part is good. Control Z. Now let's focus on this. Okay. Look, I consider blue empty. At first, I know that the hole can be only in blacks if you consider black and white. And now I consider like this, these blacks, and let's consider with blue these things. I want to see, for example, which holes can be reached from each other. So we consider this blue, and then for next layer, I consider they are green, okay? Or let's consider, for example, they are red. I want to prove, and both, if you consider black and white, both blues and reds are black. But if, for example, our hole is on blues, it cannot be on reds. Okay, we will prove it. Then in next layer, we have these blues. We are solving layer by layer. And in next step, we have these reds. And then, right. Next step, we have these blues. And in next step, we have this red. Okay, so here we consider it is 1 to 2k plus 1 or 1 to 2k plus 1. The number of blues we want to calculate. As you can see, we have how many rows, how many columns? 1, 3, 2k plus 1, it will be 2k plus 1 minus 1 over 2. Look, because recursive, it is arithmetic progression. Last one minus first one over common difference plus 1. This is squared because we have exactly this number of rows, this number of columns. So it will be what? K plus 1 whole squared. Number of red is what? We consider it's from 2 to 2k. And also for rows, 2 to 2k. And the intersection of these columns and rows. Intersection, blue cells or intersections of odd rows and odd columns. Red cells are intersections of even rows and even columns. So it will be what? It will be 2k minus 2 over 2 plus 1 whole squared. So it will be what? It will be k minus 1 plus 1 whole squared. So it will be k squared. Now we can understand something. We can understand. And I want to say that if in one configuration the first hole is blue, then if you reach any other configuration, the whole cell will be blue. The reason is what? If you can see, for example, if one, for example, we consider one blue in general. If one domino comes to this one, we have 4 direction in general, and then this whole change to other blues. Okay. Also, if you move this, move this, move this. So blues and reds we can say are disconnected parts. So we have blues here and the reds here. So the number of holes can be what? The number of cases, the number of holes can be at most k plus 1 squared. Because here, how many blues are there? We know k plus 1 squared. How many reds are there? K squared. So if we are here, we can only move between the configuration here, between the holes here. If we are here, we can only move between the holes here. So we can say the answer is at most k plus 1 squared if we use all our blues. If we use also all our reds, because we can only use reds, it will be k squared. So we proved our answer is at most k plus 1 squared. Now we should focus on last part of the problem. That's lemma 3. K squared plus 1, k squared plus 2, 2k squared plus 2k, because k squared plus 2k plus 1 is k plus 1 squared, or bad. Okay, if we prove this, the problem will be solved because we've considered all other numbers. Now, if you want to use, there are more than k squared. If you want to use this by this proof in lemma 2, we should use blue holes, because if you use red holes, if you use all of them, it will be k squared. So we have to, so our first hole, let's prove it by contradiction, suppose it's possible. So our first hole is blue. Okay, now let's reject. I want to prove that if more than k squared, for example, k squared plus 1 blues can be reachable, then all of them can be reachable, and the answer has to be k plus 1 squared. Suppose it's not possible, so we say, okay, if you consider the blues, let me tell you something. For example, I want to draw a graph that, if for example, we have a cell, like, let me tell you. Okay, let's consider the blue cells that are reachable. For example, in part A, the blue cells that are not reachable, let's consider reachable, the are not reachable n, okay, in group. So we know the numbers here is greater than equal k squared plus 1, and the number here is at least 1. Okay, now we want to focus on n, and we want to reach contradiction, because these holes are not reachable. I define a direction It means what? If we have, for example, only I want to consider this direction on n. For example, suppose without lots of generality, suppose, for example, this hole is in n, okay? Then it is covered like this or like this, any of them. It is not important. Without loss of generality considered from left to right. Then you define a direction from hole to the cell that is not hole. Okay? So it is this. When we have, for example, we consider it for all holes. Also for red holes, we define it for all things. We have direction. For each domino, we have direction. So if it is, for example, hole, it is not, we consider this direction. For example, if it is vertical, if it is this, you consider this direction. From hole to the cell that is not hole, okay? And we know the holes are in black cells. It means what? From, for example, black cells to white cells, black cells to white cells. Because each domino occupy one black, one white. You consider the direction of each domino from black to white. Now we can consider what? Each domino or each hole. If we consider this hole, each hole has a direction or each domino. And as you can see, the direction is to another hole. Except what? Look, for example, if you consider this one, again, it is to another hole, the direction. Except the case that, also for this one, it is for this, or the bad case is the direction is like this. For this one also, you can say it is connected to this one or it is connected to this one. The bad case are these things that it is, and this one is not connected to any other hole. So because I want to say it is correct for all things, I define some red holes in these parts. Okay. Now in this case, we can say any direction is to another hole with the same color. Blue to blue, red to red. Okay? Now I consider what? I say each of these things have a direction to another hole. So this hole to another hole. And we know that it doesn't have direction to this because this hole is reachable if we have direction. For example, this direction, it is in n. It is in r, it is contradiction. Because look, this one is reachable, you can move this, so n is also reachable, contradiction. So we have direction only from this thing to these things, okay? So it's like a graph, the vertices are the holes, and the edges are like this. Now, so we have direction from this to this one. And the next thing I want to say is that in a graph, if all vertices have degree out degree 1, then we define it by this. For any vertices in I, in n out degree is 1, exactly 1. So we can say we have a cycle, directed cycle. The reason is what? Because you say, okay, it is the first one is connected to another one, the second one connected to another one, the third one connected to another one, because out degree is 1. We can have this for infinitely many times because n is constant. The number of n, we have a finite number of cells here. So there is a case that it is connected to something, we've seen that before. Then it will be a cycle. We consider this as a cycle. Now, another thing I want to say, that if you consider, for example, this direction, on both sides we have red cells, okay? Also, because we've added these reds, if we have this, for any direction, on both sides we have red. And now, when we consider this cycle in n, because on both direction we have red, so there is a red inside that, okay? And exactly, you can say same proof for red. You say, okay, each red cell is connected to another one. Okay, so let's consider the reds like this. And the cell that is inside is a real red cell because these cells were not real and they are outside this cycle. Any cycle with blue holes, these red cells outside will be outside the cycle. So we have some real cells inside. And for example, consider these cells, for example, T. Now, again, you can say, okay, out degree is 1 again. Why? Because it is connected. For example, the domino is this. Again, you define this one. and it is connected to this one. So you can say the same thing again. We have a cycle inside that, and the thing with that we can say again, for each red edge we have blue on both sides. So again we have some blues inside that. And let me tell you something, the only vertex here that doesn't have any out degree is the first cell that is not covered, because no dominoes covers that. So for that vertex we can say, for example, it doesn't have out degree, but the other cells have out degree, and we know the main empty cell is in R. So when we consider N, because all of them has out degree, it is 1. In R, it is not necessarily that we have a cycle. So it is in N. Now it is on red parts. And now, if you consider the blue cells that is inside this, we know that, again, we have a cycle, blue cycle. Why? Because here, the blue cells that we don't have this main cell here. Because look, when we have, for example, the cycle like this, it blocks inside and outside. We don't have any direction from inside and outside. So when it blocks this one, we know it is greater than k squared. And if you consider, for example, the whole cycle like this, the greatest cycle, inside that, it is not greater than k squared. Okay? For this one, it was k plus 1 squared. For this one, it was k squared. It will be k minus 1 squared. So it's not possible that let me write that. The main cell, it's not here, because then it won't be greater than k squared plus 1, the reachable. It is inside and it will be small. Now, this one again is in N. And again, we can do the same thing. And we will see, okay, we have another cycle. Again, on one side we have red, on one side we have blue. And you can consider another red inside with same proof. You can continue and continue and reach contradiction, because you can't do it for infinitely many times, because length of cycle will be decreased. And also you can say, also if length of cycle, we don't want to prove if length of cycles will be decreased, we can say something. For example, you can consider some blues here, again some reds, some blues, some cells, some reds. The number of holes is finite. How many blue holes are there? K plus 1 squared in all. And the number of N is also less than, is finite. So if you consider this is in N, it is in N for infinitely many times, you can't do this. So we've reached a contradiction, and we can say, okay, it is not possible to have greater than equal k squared plus 1. Okay, let me write some homeworks for you to solve with same idea, the approaches. We've considered a small example, we found the idea, step by step it wants to find all cases. So, and for example, for maximum case, we've proved that it is reachable and cannot be greater than that. It is also important. As homework number 1, try to solve this. As homework number 2, try this. And also in other problems, I solved more than one problem of this here with considering small example. In other problems also, after the solution, I released some homeworks from BMO British Mathematical Olympiad. You can work also on them. So there are some important approaches in combinatorics. Number theory start from what place, considering what. For example, in number theory, when we have product of two numbers equal to perfect square, these things are important. If you want to learn these ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. In this video, we want to solve problem that is in common with USAMO and USJMO. It's for junior. It's question problem number 4 of USAMO, United States of America Mathematics Olympiad, and question number 5 of USAJMO, which is for juniors, and 2023. The problem is the combinatorics problem, and in this problem I want to tell you so much famous idea, and I will leave some homework at the end of the solution. The idea, I can say, one of the most useful idea, especially in combinatorics, also in other topics can be useful. So let's start. It says a positive integer a is selected. Okay, so a belongs to positive integer. This sign means belongs. and some positive integers are written on a blackboard. Okay. So for example, we have x1, x2 to xn, or because we have n here, xm on blackboard, they are positive integers. It says Alice and Bob play the following game. On Alice's turn, she must replace some integer n on the blackboard with n plus a. So a, change n, she adds a, and it will be n plus a. And on Bob's turn, it must replace some even integer n on the board with n over 2. So divide by 2, n over 2. N is even. Okay. Alice goes first. It is important who plays first. And then they alternate turns. If on his turn Bob has no valid moves, the game ends. It means what? It means all numbers are odd. Okay? Then Bob cannot play. After analyzing the integers on the board, Bob realizes that regardless of what moves Alice makes, he will be able to force the game to end eventually. Okay, means Bob can do something to reach a situation that all numbers are odd. Show that, in fact, for this value of a and these non-integers on the board, the game is guaranteed to end regardless of Alice's and Bob's move. It means what? If Bob can reach a situation that all numbers are odd and it's the turn of Bob and Bob should play. Means the game has finished. Then it says we should write this. The game is guaranteed to end of Alice's or Bob's regardless. Alice's and Bob's move. It means that eventually, regardless of Alice's and Bob moves, all numbers will be odd. And it's not important that Bob did what, Alice did what. Okay, for this problem, because we want to understand, this problem is a little hard to understand. The most useful idea that we want to use here, we want to consider a small example. Now, a small example on what? We can use a small example on A, on the numbers. I use a small example on M, the numbers that are on blackboard. Suppose M is 1. So we have one number on blackboard, X. Then in next step, the problem says Alice goes first. So it goes to plus A, X plus A. Then Bob divides by 2. It will be X plus A over 2. I want to first analyze the case that, for example, it doesn't stop. It goes up to infinitely many steps. Let's analyze that case first. Then it will be plus A, it will be X plus A over 2 plus A. Or we can write it as X plus X over 2. And look here, Alice plays, here Bob plays, here Alice plays. X over 2 plus A over 2. In next step, Bob divides by 2. So it will be X over 4 plus A over 2 plus A over 4. And then in next step, Alice adds A. It will be X over 4 plus A over 2 plus A over 4. Again, Bob plays. Okay, so and so on. Now let's add one more. For example, Bob plays X over 8 plus A over 2 plus A over 4 plus A over 8. And then Alice adds A. It will be X over 8 plus A over 2 plus A over 4 plus A over 8. Now, and so on. If, for example, this we want to consider the case that it can go up to infinitely many steps. It means what? When it is Bob's turn, the number should be even. And let's consider those steps. Here, x plus a, Bob wants play here, x squared plus a over 2 here, x over 4, here this one, and here Bob wants play. Now, in this step, as you can see, these numbers should be even because Bob wants to divide by 2. So in general, we see, okay, let's check. X plus a should be even. In next step, x over 2 plus a over 2. X over 2 plus a over 2. It will be x over 2 plus 3a over 2. It means that x plus 3a over 2. It should be multiple of 2. Next step, x over 4 plus a over 2 plus a over 4 here. It should be even, and if you factor from 4a plus a, 2a, 6a, 7a, x plus 7a, it is even. This number is even. This number is even. And then this one. X over 8 plus a over 2 plus a over 4 plus a over 8. Then we consider common denominator 8. It will be x plus 8a plus a 4a 12a plus 2a 14a plus 1a 15a over 8. And now let's consider in general. This number also should be even. So we can say x over 2 to the k plus a over 2 plus a over 4 up to a over 2 to the k. Okay, if we consider this, we factor from 2 to the k, we use common denominator and it will be x plus a times 2 to the k plus 2 to the k minus 1 plus 2 to the k minus 2 up to 1. And for calculating this, it is famous identity. You should memorize it in this formula, 1 plus r squared to r to the n equal to r to the n plus 1 minus 1 over r minus 1. There are around 5 important and basic identities you should memorize. One of them is this. So if you apply it here, this one, r is 2 for this identity and n is k up to k. So it will be x plus a times 2 to the k plus 1 minus 1 over 2 minus 1. All over 2 to the k. This number should be even, like previous terms. Look, we don't write these things on our answer sheet. We are analyzing, and these things are for ourselves. We want to find the idea and then generalize it for the. We want to find the idea and generalize it for general m. M was the numbers on the blackboard. So x plus a times 2k plus 1 minus 1 over 2 to the k. This number is even. When it is even means it is, for example, 2t. So if you multiply both sides by 2 to the k, then x plus a times 2 to the k plus 1 and expand here minus a should be 2 to the k plus 1 times t. And then x minus a is equal to 2 to the k plus 1 times t minus a. This part is multiple of 2 to the k plus 1, so we conclude what? We conclude x and a, x minus a, is multiple of 2 to the k plus 1. A is what? A is the number that we add each step. Alice writes that number plus a. X is what? Is the first number. They are constant. So when a constant, and for any k, for all k, it can go to infinity. So, okay, it can go to infinity, and what's that? We have only one number, one integer that is multiple of all large number. It's what? 0. Only 0. So x minus a should be 0. So the only case that it goes up to infinity, it doesn't stop, it won't stop, is x equal to a. And let's analyze it. So the first number is a. Alice adds a, it will be 2a. Then Bob divides by 2, it will be a, and so on. Alice adds a, 2a, Bob divides by 2a. And we have a cycle. Okay, so we've understood that for n1, what happens? So let's prove the problem for n1. If it stops, because we have only one number, if they have to do the thing, for example, in first step, Alice have to select this one because we have only one number, and the problem is correct. If it ends, it doesn't relate. It is not related that they play, for example, like they play what regardless of their playing. It will be stopped. Okay, so for n1 we've considered m1. Now consider we have two numbers or more. If you have more numbers, for example m2, you have some numbers like x1, x2. Okay, so let's analyze first m2, and then in m2 we can find completely the idea of the problem. Here, suppose that, for example, Bobs can do something that for example, we reach a situation that for example, the game will be stopped. In that case, we can say what? They can reach a situation that it is odd, and it is Bob's turn. Okay, and he cannot play. So it means Alice reached these two things. And the problem says Bobs can do something to reach this situation. But if you consider, because Alice always adds a to one of the numbers, if a is odd, it cannot happen. Why? Because in this step, for example, suppose we had x1 prime, x2 prime. Let's consider the cases. x1 prime, x2 prime. If it was odd, or odd, even, or even odd is same as odd, even, even. In this step, Alice can add a to one of them, then we reach e or not o. In this step, Alice can add odd to this one, it will be odd, and in this case, Alice adds a to one of them, it will be odd even. So Alice can do something to not reach o. So if a is odd, it's we reach contradiction because it says Bob can do something. Bob can do something to reach a state that all the numbers are odd. So lemma 1. Look, when we reach any good thing, we write it as a lemma. For example, maybe we reach 8 lemmas. Okay? We don't know which of them useful at the end. You should write all of them. For example, you write 10 lemmas. At the end, you will say, okay, 5 of them, 7 of them are useful, 3 of them are useless. Okay? Because now we don't know which of them are useful. We write anything that maybe can be useful. So, A is even. The first thing that we can consider. Now let's analyze the case. If one number is a here, like we want to use m1. Okay, in m1 we said if they are equal, then it won't stop. So suppose if one of the numbers are a, Alice can add a here. It will be 2a, and then if Bob doesn't divide this by 2, Alice can play with other number. For example, it is the thing here. I said a is even. It's also useful for any m, not only m2, because we are working on m2. So here, look, if one of the numbers are a, Alice adds a. If Bob doesn't divide it by 2, for example, divide something else by 2, for example, second number, then Alice works here until Bob has to eventually work on this 2a, because Bob wants to reach a state that all numbers be odd. So when Bob divides this one by 2, it will be a, and then Alice adds again by a, 2a. So again, if Bob, for example, doesn't divide this by 2, work on other number, Alice also work on other numbers, adds plus a, and then if Bob divide this again by 2, Alice adds a. Okay, so here we conclude, because from assumption of the problem, Bob can reach a state that all numbers be odd, but by this state, he cannot. Why? Because Bob can reach a state that all numbers are odd and it is Bob's turn. But as you can see, Alice adds A and it will be 2A, and now it's Bob's turn. So lemma 2, xi are not A. Okay, our numbers are x1 to xm, so none of them should be A. We've reached this one by using m1. We've considered that. Now, if we consider this one, as you can see, for example, it was A plus A, 2A, and something like this. We can say, suppose, for example, we have instead of A, 2A. Okay, if we want to say also 2A is bad. Why? Because if you have 2A, Alice doesn't do anything with this, adds other number plus A plus A. Now, eventually Bob should change this because Bob wants to reach a case, all numbers should be odd and it is Bob's turn. So Bob divided by 2A, and again like previous one, Alice adds A to A. Again, if Bob doesn't divide by 2, Alice works on other numbers until Bob divided by 2 again, and then Alice adds A. Okay, so 2A is also bad, and we can generalize it. 2 to the k times A also it seems to be bad. Why? Because Alice doesn't do anything to this number, then Bob has to divide it by 2, and then it will be 2 to the k minus 1A. Again, Alice doesn't do anything with this. Bob should divide by 2 until the case that Bob divides by 2 and reach A. In this case, Alice adds A. It will be similar to previous proof. So, lemma 3. xi shouldn't be 2 to the k times A. Now, because we have 2 to the k, we guess that maybe we should work on v2 of these numbers. V2 of a number is what? V2 of, for example, a number S is maximum power of 2 that divides S. Means what? For example, V2 of 12 is what? Is 2 V2 of 12 is 2 squared times 3. And look this part. It's 2. Maximum power of 2 is 2 to the 2 that divides 12. 2 to the 3, 8 doesn't divide this. For example, V2 of 30 is V2 of, it is 2 times 3 times 5. The maximum power of 2 that divides this is 1, because 2 to the 1 divides 30, but 2 squared doesn't divide this. Okay. Now, let's consider, for example, the case that we want to work on x1. We said x1 shouldn't, on one number, for example, xi, any number, for example, without loss of generality, let's work on x1. We said x1 is not 2 to the k times A. So, suppose v2 of x1, and we know A is even, by lemma 1, A is even. Suppose v2 of x1, because, let me tell you something. When we have, for example, x1, then if Alice plays x1 plus A. If v2 of x1 is less than v2 of A, for example, means what? For example, x1 is 2, but A is 8. So 10. Look, v2 of 2 is 1. It has only the power of 2 is 1. Again, here is 1. Again, for example, if for example we add 8 to this one, it will be 18, and the power is what? The power of 2 is 1. So, let's consider something. If v2 of x1 is less than v2 of A, let's see what happens. In this step, I want to say that if we work on x1, power of x1 cannot be increased. Why? Because at first, if it is Bob's turn, we have some numbers also. For example, maybe Alice plays with other numbers. If Bob divides by 2, then here we have x1 over 2, if it is not odd. I want to say that Bob can do something that reach to an odd number by starting from x1. Why? If x1 is odd, then it will be okay. I want to say that only for x1. If we want to only focus on x1, Bob can reach an odd number here, and then in next step also it will be odd if we do anything to this. We want to prove this. If we reach an odd number, then Bob cannot do anything, and if Alice do anything, she adds by A, and because A is even, odd plus even is odd. So I want to prove that in this case, Bob can reach an odd number, and then after that, we proved here all of them should be odd. If x1 is odd, the problem will be solved. If x1 is not odd, if it is Bob's turn, Bob divides by 2. If it is not Bob's turn, Alice adds by A. So in this case, what happens? We have x1 plus A. I want to prove v2 of x1 plus A equal to v2 of x1. Means the v2 won't be increased. And in this case, v2 of x1 over 2 obviously is v2 of x1 minus 1. So if Bob plays, and Bob decrease v2 of x1, v2 of the number by 1. If Alice plays, v2 won't change. So here we can conclude each term, each step that Bob plays, Bob decrease by 1, and Alice cannot increase this v2 of that until Bob divides by 2, to reach an odd number. And after that, this number is useless. Bob can work on the other numbers. Let's prove this one. Because v2 of x1 is less than v2 of A, we can say x1 is 2 to the, for example, t times r1, t1, r1, that r1 is odd, okay? It means we consider it as t1. And now consider it as t2. So A is 2t2 times r2, which r2 is odd. And we know t2 is greater than t1, okay, from here. So x1 plus A equal to 2t1 r1 plus 2t2 r2. And if we factor, because t1 is less than t2, if we factor from 2t1, it will be r1 plus 2t2 minus t1 r2. Because t2 is greater than t1, this part is even. Because it is odd, this part is odd. Odd times 2 to the t1. This number, v2 of this number, will be t1. So v2 of x1 plus A is t1. And v2 of x1 was what? t1. Okay, so we've proved that if v2 of x1 is less than v2 of A, Bob can do something to reach an odd number. And for this number, Bob can do something to stop this case. Okay, so let's call this lemma 4. Lemma 4, if v2 of xi is less than v2 of A, Bob can change this number to an odd number eventually, and after that step, the number is always odd. We proved this. Okay, now consider the case that v2 of xi, for example, equal to v2 of A. We want to see what happens. In this case, xi. If it is Bob's turn, Bob divides by 2 if it is Bob's turn. Bob divides by 2, and we reach xi over 2. And we know it is at least 1 because A is even from lemma 1. So we know because A is all even, xi is also even. If we divide by 2, if Bob's divide by 2, then it will be this, and v2 of xi over 2 is v2 of xi minus 1, and it is less than v2 of xi, which is v2 of A. And because v2 of this number that we reached is less than v2 of A, it will be like lemma 4. By lemma 4, Bob can reach an odd number. By lemma 4, Bob can reach two odd number, 2 O. But if it is Alice's turn, then we can say what? Xi, Alice adds a. It will be xi plus a. Now I want to consider v2 of xi plus a is what? Suppose here, let's consider this, it is t3. So xi is what? Is 2t3 r3. A is what? 2t3 r4, because power of two of them are equal. Now xi plus a will be what? You can factor, it will be 2t3 r3 plus 2t3 r4. So it will be, if you factor from 2t3, it will be r3 plus r4. Odd plus odd is what? Is even. Okay? So we conclude that v2 of xi plus a is greater than v2 of xi. And because v2 of xi is v2 of a, we've reached the case that the power of this part is greater than power of a. So we should analyze the case that power of the number that we have is greater than power of a. So let's consider this case first. If v2 of xi is greater than v2 of a, in this case, we say, okay, if we have xi, if Alice plays and adds by a, then if you factor from this, for example, x, it will be xi plus a. When the powers are not equal, like this, the sum will be v2 of that will be equal to a smaller one. And easily we can prove by the form that I've showed you here. By this form, 2t3r3. And so let me tell you the reason is what, for example, suppose this one is w1, w2. So v2 xi is 2 to the power of, for example, w1 times r. For example, without loss of generality, consider r1 because it's not related to previous one. And a, for example, is 2w2, r2, r1, r2 are odd, so xi plus a is what? 2 to the w1 is 2 to the w2 is a smaller one, so we can write 2 to the w2 r2 plus 2w1 minus w2 r1. This part is even, this part is odd, so sum of them is odd, so we conclude v2 of xi plus I is w2 as I said here. Now here we've reached this step again. So let's see what can we say. I want to prove that if v2 of xi is greater than equal v2 of a, Alice can do something to, for example, Alice can do something that always that number be even. Why? Let's see. Suppose at first the number we start with this part. v2 of xi is greater than this. Alice adds a. Now we know v2 of xi plus a equal to v2 of. If we have this, I think if she does here, then Bob can divide by 2 and then it will be bad because v2 of that will be less than v2 of a. So let's do something. Alice doesn't do anything. Suppose v2 of xi is greater than v2 of a. Alice only adds to other number, for example by a. Eventually, because Bob wants to reach a state that all numbers be odd, so Bob should divide this one by 2, xi by 2. Alice waits up to the case that we reach to the state that v2 of this number equal to v2 of a. Okay, means xi divided by 2. Here we have 2 to the w1, w1 minus w2, because 2 to the w1 minus this is 2 to the w2. So Bob divides by 2 up to this part. Now, in this case, v2 of this number xi over 2 to the w minus w2 equal to v2 of a. In this state, Alice adds by a. We've analyzed this here. Then this number v2 of xi plus I will be greater than v2 of a. Alice adds by a. 2 to the w minus 1 plus a. Now v2 of this number again will be greater than a. Okay, it will be similar to v2 of xi. Again, Alice doesn't do anything, adds other things by a up to the case. For example, divides by 2 to reach the case that again we reach a number, for example L, that v2 of L again equal to v2 of a. In this state, Alice adds again by a. And then L plus a, v2 of L plus a will be greater than v2 of a. And again, Alice doesn't do anything, works on other numbers, and then Bob should divide by 2 up to this. And with this way, Alice can do something that Bob cannot reach, an odd number by starting from xi. Okay? So we've proved that lemma 5. Because the problem says Bob can reach a state that all numbers be odd. With lemma 5, we should say for all I, v2 of xi are less than v2 of. And now, if this thing happens, we can say it satisfies assumption of the problem. Why? Because if we start from x1, by lemma 4, Bob can reach a state that this number be odd. Then this number is always odd. Bob doesn't do anything with this number, then it starts with x2. If x2 is not odd, Bob focus on this and reach it to odd numbers, and then up to xm reaches to odd number, then all numbers are odd. And for example, if it is Bob's turn, the game will be stopped. If it is Alice's turn, Alice says add by a. Again, it is odd because a is even from lemma 1. And now it's Bob's turn, and Bob cannot do anything. Okay, so we've reached this. Now we should prove what? We should prove. We know v2 of all numbers are less than v2 of a. We should prove that it is not important Alice do what and Alice does what and Bob does what. Always with, regardless of their playing, they reach all m odd numbers. Let's prove this part. If it is x1, we know v2 of x1 is less than v2 of a. Suppose it is x1, x2 to xm. I define a function f. Defining a function is so much useful in many problems. Also, BMO for UK, for USA, for IMO, I define this function v2 of x1 plus v2 of x2 to v2 of xm. When these are the numbers x1, xm, I mean the numbers on the blackboard, sum of v2 of them. If Alice plays, it will be x1 plus a. v2 of this number won't change. But if Bob plays, it's not important. Divide this one by 2, this one by 2, this one by 2. He divides one of them by 2, one even number. And then it will be x2 by over 2, and v2 of x2 will be decreased by 1. So after Alice plays and then Bob plays, for example, suppose f is c. In this step, f will be c minus 1. Again, it is not important. Alice does what, Bob does what. Again, f will be c minus 2. And f cannot be negative, because if all of them be odd, f will be 0. And because f is at least 0, we know that there is a step that it will be stopped. We will reach f0, Alice plays, Bob plays. And after this step, Alice plays. Then Bob cannot play, because f is 0 means all numbers are odd and Bob cannot do anything. Okay, this problem was a good application of considering a small example. Let me write some homework for you. For example, I can write from IMO. We have also some problems you can do as homework. Also from BMO, which is British Mathematical Olympiad. Let me write. So solve this problem. You can solve it with a small example. It is for IMO 2020. And the next problem that you can do as homework is problem of BMO. It's for UK. I also released the solution of this for the first time. It is for British Mathematical Olympiad Round 2, 2023. Okay, last BMO Round 2. BMO and USAMO are two most prestigious National Mathematical Olympiad. It's good to work on both of them. It helps you. Also, for other example, other national Olympiads, International Mathematical Olympiad, this is the most important idea. Consider a small example, analyze the problem step by step, and try to gather tiny things you've proved, and then prove the whole problem. And as you can see, I proved many lemmas. Xi equal is not a was not useful, but xi is not 2 to the ka also was not useful. This one was useful. Okay, but they helped us. Okay, as I said, at the end you will understand which of them useful, which of them are not useful. Okay, so analyzing the problem is so much important. Okay, if you want to learn important ideas, for example, considering a small example, how to approach a problem, important ideas and formulas you should memorize, you should learn them in geometry, combinatorics, number theory, and algebra, feel free to send message to my WhatsApp number in the description comments, and try to solve these two homeworks. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. Bye. In this video, in this part, let's say we want to solve fifth problem of USAMO. We want to 2023. We want to analyze the problem. The problem needs what? How to approach this problem, because the way we want to approach this problem again is one of the most useful approaches. And let's see. And after that, after solving this problem, I will leave some problems as homework. You can solve with same idea from different national Olympiads and also from IMO. So let's read. It says let n be greater than equal 3 be an integer. We say that an arrangement of the numbers 1, 2 to n squared in an n by n table is row valid if the numbers in each row can be permuted to form an arithmetic progression, and column valid if the numbers in each column can be permuted to form an arithmetic progression. For what values of n is it possible to transform any row valid arrangement into a column valid arrangement by permuting the numbers in each row? So when we want to solve this problem, the first thing you should check is to consider a small example for n3. Let's check. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's consider. We want to consider is it possible or not. So consider the row that contains 1. So we know, because the problem says at first we have a row valid table. So the row that contains 1, you should have an arithmetic progression. So it is 1, 2, 3, or if the common difference is 1, plus 1, plus 1, or we have 1, 3, 5, if the common difference is 2, if the common difference is 3, 1, 4, 7, if the common difference is 4, 1, 5, 9, if the common difference 6, it's not possible because it will be, if common difference is 5, it will be 6, 11, because we have up 1 to 9 only. So for 1, 2, 3, the numbers that are left are what? Let's consider first case, let's write third, fourth case. In first case, what numbers are left? 4, 5, 6, 7, 8, 9. Now, we can say, okay, the next one, for example, is 4, 5, 6, or let's write 1, 2, 3. If the difference for 4 is common difference is 2, so 4, 6, 8. The common difference 7, 3 is not possible. 4, 7, 10. And as you can see, the rest will be unique. Why? Because 3 numbers are left. For this one, 7, 8, 9. For this one, 5, 7, 9. So we have 2 cases in case number 1. Case number 2, 1, 3, 5. What are the numbers that are left? 2, 4, 6, 7, 8, 9. Now, here, we say, okay, if the common for 2, if the common difference is 2, you say, okay, 2, 4, 6. If the common difference for 2, it cannot be 3 because we don't have 5. The common difference is cannot be 3 because we don't have 5. If it is 4, 2, 6, the next one 10. It's not possible. So the only possible case 2, 4, 6, and then 7, 8, 9. If we have 1, 4, 7, then we have 2, 3, Let's write 5, 6, 8, 9. Okay, if the common difference be 1, starting from 2, 2, 3, 4, we don't have 4. So if we consider 2, 5, 3, 2, 5, 8, one case that is possible, let's write 2, 5, 8. Then if instead of 5, we consider 2, 6, 4, 10, it's not possible. Okay, so 2, 5, 8, and 3, 6, 9. It is another case, and now let's consider last case. 1, 5, 9, the numbers that are left are 2, 3, 4, 6, 7, 8. One case you say 2, 3, 4 if the common difference is 3 and the rest will be 6, 7, 8. If the common difference is 2 starting from 2, 2, 4, 6, then 3, 7, 8 is not good. If the common difference is 4, it's not possible again. So we found 1, 2, 3, 4, 5 cases to check. Okay, without loss of, let me tell you one case that you should check without loss of generality. For example, for this one, you say, let's consider it is 1, it is 2, this case is 3, this case is 4. For case number 1, without loss of generality, because you can permute the numbers in the row, so 4, 5, 6, 7, 8, 9. Now we want to, so this arrangement is good. 1, 4, 7, the common difference is 3, 2, 5, 8, 3, 6, 9. So first one is okay. So look, for example, maybe first row is not 1, 2, 3, it's 2, 1, 3. The problem says you can permute the numbers in the row. So I can say I permute the first row 1, 2, 3, 4, 5, 6, 7, 8, 9. And it is not important that 1, 2, 3 is in the first row or second row, because column valid means in each column you can permute to reach an arithmetic progression. Okay, so first one is okay. Now let's consider second one. So let's paste it here for 2. Again, we consider 1, 2, 3 and 4, 6, 8, 5, 7, 9. So let's see. If I want to consider 1 with 4 and 7, it's good. If you consider, you will see, then I permute after this section. I want to find first numbers that are good with each other. 2, 6, not good. 2, 5. Okay, if we consider here 1, 4, 7, we can consider 1 and 2, 5, 8 is good, and 3, 6, 9. And look, because it is good, you can permute like this. You say, okay, we consider 1, 2, 3, and 4 here. 8 is good for this part. 6 here. 7 you move it here. 5 is green for this column, and 9 here. Now you can see 1, 4, 7, common difference 3, 2, 5, 8, common difference 3, 3, 6, 9, common difference is 3. So 2 is okay. Okay. Okay, now let's consider third case. Okay. For third case, this one. If we consider it is 1, 4, 7 first, 2, 5, 8, and 3, 6, 9. So, if we consider 1, 2, 3, 4, 5, 6, 7, 8, 9, I think it's good, because look, if we consider 1, 2, 3 here, then 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay, so common difference in each column is good. We don't need to permute. Let's consider last case, fourth case. We say that it is 1, 5, 9 in first row, 2, 3, 4 in second row, 6, 7, 8 in third row, and then we can consider 1. 1, 2, 3 is not possible because 2 and 3 are here. 1, 3, 5 also not possible. 1, 4, 7 possible. Then 258 is good. 369. Again, like this part, like this case that we permuted, you should permute such that all reds be in first column, all greens in second column, and the others are on last column. So 3 is good, okay? And 3 is good. Now we want to check N4 to see, can I find an example that doesn't satisfy the condition? Okay, in this case, let me tell you something. If we consider, for 1, suppose first column be, for example, 1, 2, 3, 4. Then if I want to create an arithmetic progression, I say, okay, if 1 starts with 5, then the next one plus 4. 9, 13, 1, 2, 3, 4. If the common difference is not 4, is 5, then we can say 1, 6, 11, and 16. Okay, so here I want to see, can I find a counter example? If I place 5, 6, 7, 8 here, and 8 numbers are left. So, in this part, let's consider 9, 7, 11, 13, and then 8. We had 8, so 10, 12, 14, 16. So 1, 5, 9, 13. 9 and 13 are in third column, the third row, so this one is not possible. So we should select 1, 6, 11, 16. 1, the only possible case. 6, 11, 16. Now for 2. For 2, if I take common difference, because 2 up to 3, 4 are in same row, the next one can be 5, or is for 1, 7, and let's check, for example, 2, 5 plus 3, 8, 11, but 5 and 8 are in same row. For common difference 5, it will be 12 and 17, and it's not possible. Why? Because we have up to 16. Okay, let's check 5, 5, 5. Okay, so it is a counter example for N4. Now we guess first. Maybe odd numbers are good, even numbers are bad. So let's check. We want to generalize N4. I want to use this. I want to reject first even numbers. It means find a counter example for each of them. With the same way, I want to reject 6, then I want to reject 2k, and then I want to reject another numbers. By exactly this way, for n6, I consider 6 by 6 grid. Okay, so let's consider here again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, like previous time, here we considered all rows except last 2 rows, or the common difference is 1. Let's consider common difference D. It is 1. It is 1. It is 2. It is 2. I want to consider except last 2 rows be 1, then here be 2. So 25, 27, 29, 31, 33, 35. And this for 26, 28, 30, 32, 34, 36. Now let's consider again like previous time. We say 1 can come with 7, then common difference is 6 because 1 to 6 are in the same row, so the first number after 1 for the columns can be 7. 1 7 plus 6 13 and 19 25 and 31. 1 2 3 4 5 6 numbers. The next one is 1 8 plus 7 15 22 29 36. So as you can see, common difference 7 is not possible for if we want to select 1. We want to select 6 cells in each row, exactly 1 cell to, for example, select like this part, red, like here. Okay, let's see which of them possible, which of them not. In previous case, the first one was not possible. The reason was what? 25, 31, the last two odd numbers. Here also, we will see 25, 31 are in this row. So the first case is not possible, so only second case is possible. Let's select them. 1, 8, 15, 22, 29, and 36. In previous case, we've reached contradiction by 2. Now let's consider here what are the possible cases for 2. If the common difference is, if the first one after 2 is 7, the common difference 5, it cannot be 8 because we have it here. 2, 9, let's see how many cases. I wrote 2 cases. Okay, let's check. If you check 2, 9 plus 7, 16 plus 7, 23 plus 7, 30, and plus 7, 37. Again, we've reached contradiction because we want to select 6 numbers, one more than 36, and here one more than 16, so it's the same way. And if we consider this case, the only case that is left, 2 plus 5, 7, plus 5, 12, plus 5, 17, plus 5, 22, and plus 5, 27. And in previous case, why we reached contradiction for this case? Because 11 was selected. Here, the last one, 27, not selected. So let's check. 2, 7, 12. 7 and 12 are in same row. Let's see. Did we have also this contradiction? Oh, yes, 5, 8. Okay. So here and okay. 17 was here. 22, 27. Also another contradiction like previous time. 22, we've selected 22. Okay, we've rejected this with 2 ways. Now I want to, let me tell you, generalize this to 2k. Okay? I want to reject 2k in general. Okay, suppose it is 2k by 2k. It is first, second column, 2k, 2k minus 1. And then I, like previous time, 1, 2, 3. It is 2k. It is 2k minus 1, 2k minus 2, 2k minus 3. So I select 1 here, 2 here, to 2k. Then 2k plus 1, 2k plus 2. Look, the common difference is 1 for all of them except last 2 rows, 2, 2. So here up to 4k, you write the next one 6k, and this part, look, third row times 2k, and this one, I think I should, let me maximize the table. Okay, now it's better. So it is 1, 2, here it is 2k, 2k minus 1, 2k minus 2, and here is 1, 2 to 2k. So first you consider, okay, common difference here is 1, 1, 1 up to this part 1, and here is 2, 2. So you consider 1 to 2k, here 2k plus 1, 2k plus 2 to 4k. The next one is 4k plus 1, 4k plus 2 to 6k, and this part, let me tell you first here, 2k times 1, 2k times 2, 2k times 3, it will be 2k times this row, 2k minus 2. And if you want to see 1 plus what? 2k times 1, 2k times 2, 2k times 2k minus 3 plus 1. And then here, the next one. In this case, you say, okay, it's 4k squared minus 4k. You say 4k squared minus 4k plus 1. Then the common difference is to 4k squared minus 4k plus 3. And here it's 4k squared minus 4k plus 2, 4k squared minus 4k plus 4. And if you want to consider, and because it is arithmetic progression with common difference 2, we use this formula. Is so much useful, a1 plus n minus 1d. If I want to know the last one, I say, okay, 4k squared minus 4k plus 1. The common difference is 2, and it is first term, it is 2k term, it's 2k minus 1. So it will be 2 times 2k, 4k will be cancelled, minus 2 plus 1, it will be 4k squared minus 1. Minus 1, the next previous one is 4k squared minus 3 because the common difference is 1. And for this one, you say, okay, 4k squared minus 4k plus 2 times again 2k minus 1. It will be this, and 2 and negative 2 will be cancelled, 4k squared, okay? So it will be 4k squared minus 1, minus 2, and so on, okay? Now, let me erase this part. Again, I want to use the same way. I say, okay, after 1, the first term that we can have is 2k plus 1, or 1 to 2k plus 2. Again, I want to check, probably I guess that from previous part, if we can only consider these two cases, and for this case we will reach here 36, here we will reach 4k squared. So let's check. Here it is plus k plus 1 plus 2k plus 1 each case. So the next one is 4k plus 3, and the kth term is 1 plus 2k plus 1, the common difference, times n is 2k term, n minus 1d, plus times 2k plus 1 common difference times 2k minus 1. So it will be what? It will be 4k squared minus 1 plus 1, 4k squared. So exactly like the small example. And here it will be plus 2k, so you say the next one is 4k plus 1, and if we continue up to last term, let me erase this part. It will be first term plus n minus 1, 2k minus 1 times the common difference 2k. So it will be 4k squared, like here, minus 2k plus 1. 4k squared minus 2k plus 1. Okay, let's correct this. Now we want to see which of them possible. In previous cases, we've rejected first one because, for example, let's see 9 and 13 were in second last row. So here we want to, let's write the case before that because the common difference is 2k. So the next case is 4k squared minus 4k plus 1. So as you can see, 4k squared minus 4k plus 1 is here. And 4k squared, and then we have all odd numbers after that up to the last case. So it is also an odd number, and we have this here. And you can easily prove, because this number is less than this, because it is minus 2k plus 1, and greater than this, because it is 2k more than that. Okay, so these two odd numbers are in second last row. And now, if you want to write in rigorous proof, you say, okay, this one is exactly first one. This one, 4k squared minus 2k plus 1. We have all odd numbers here because the common difference is 2 after 4k squared minus 4k plus 1. If I say this odd number is between these two numbers, the problem will be solved. Means we can reject this case. You cancel 4k squared from all sides, and then we add 4k to all parts. 1 here, it will be what? 2k plus 1 and 4k minus So this part is equivalent that k is at least 0. It's obviously correct because n is 2k and k is natural number or positive integer here. 2k is greater than or equal to, which is equivalent that k is greater than or equal 1, and it's also correct. Okay, so we proved this case is not possible because these two things are in second last row, so the only possible case is here. Now, like previous time, we should focus on 2. For 2, we can say the next one can be 2k plus 1. Let's write. Okay, so let's erase this part we wanted to prove. So for 2, the next one that we can have is 2k plus 1. 2k plus 2 is not possible because we have it here. 2k plus 3. And like previous times, we can, I think here we can say the last one will be 1 more than 36. The last time will be 4k squared plus 1, we guess. So let's check. Here it is plus 2k plus 1. And up to the last case is what? Again, we use this formula. First one plus 2k minus 1 because we want to find 2kth term times common difference 2k plus 1. So as you can see, it will be 2 and the product of this will be 4k squared minus 1. It will be 4k squared plus 1, and it's not possible because the greatest number is 4k squared. And now let's check this one. In this case, how we rejected that? This and this are in same row. So 2k plus 1, here we have plus 2k minus 1. And if you add 2k minus 1 again, it will be 4k. And we want to say 2k plus 1 and 4k are in same row. 2k plus 1 and 4k are in same row. Like here, that we had 7 and 12 in same row. Okay, so here also we've reached contradiction. So we proved that 2k's are bad. Okay, so let's write it as lemma 1. Write anything that you think may be useful as lemma. 2k are bad. Now we say, okay, for 2k, we considered the last two rows because it was multiple of 2. And here k is at least 2 because the problem says n is at least 3. So 4, 6, 8, and so on are bad numbers. Now let's consider something. I said let's generalize it. Instead of 2k, let's consider it, for example, let's write ak. And here we've considered last two rows and the common difference 2. We consider now last a rows. Now we check first by a3 to see is it possible or not, and then we generalize for any a. So let's consider n is 3k, and the first number that is not even, because we've rejected even numbers, is 9. Let's check n equal to 9. Okay, now last 3 row we want to consider common difference 3. And the others common difference be 1. Okay, so let's write 1, 2, 3, 4, 5, 6, 7, 8, 9. First row. For second row, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 7, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 9, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. And then here, we consider 55 here, common difference is 3, 58, 56, 59, 57, 60. So let's write 61, 64, 67 by 3, 70, 73, 76, 78. 79, sorry. The next one is 62, 65, 68, 71, 74, 77, 80, 63, 66, 69, 72, 75, 78, and 81. Okay, now let's consider again. We want to use same proof. Again, we want to consider one. Then we don't know. We should consider 2 or 3 because in previous case A was 2. Maybe we should consider here A3. So let's check. And here it's the point that we can conclude that for any A, how we can solve the problem. So if we consider again 1, the next one can be 10. The common difference is 9. So like previous cases, let's see how many cases I wrote. 1, for example, here 7, 8, and 36. Okay. Let's consider 110, and then the common difference is 9. You consider 19, 28, 37, 46, 55, and the next one that is 9 is 64, and 73. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you consider the common difference 10, 11, 21, 31, 41, 51, 61, 71, and 81. And you will see we have only these two cases, like the case that we had A2, because we don't have greater than 81. So the next one after 1 cannot be 12, because the last number will be greater than 81. Now here, again, how we rejected for 1, we said, okay, 25, 31 are in same group, last two elements. So let's consider 64, 73. 64 is here. Let's see. 73. Yes. So again, because of these two things, we reject these. Now for this one, 1, 11, 21, 31, let's select all of them. 1, 11, 21, 31, 41, 51, 61, 71, and 81. Now, again, like previous times, we considered 2. And for 2, we've considered, let's see. The case is 7, 9. Only these two cases. Let's see here. What should we do? So this case was good. So for 2, the next element can be 10 or 11 we've used here. So 12. Let's check again. For this one, you say, okay, 12, 22, 32, 42, and the last term will be 82 contradiction. 52, 72, 62, 72, 82, and it's bad. And we have 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. For 10, for 2, 10, you say, okay, 2 plus 8, 10, 18, 26, 34, 42, 50, 58, and plus 8, 66. Okay, so for 2, how we've rejected that? With these 2 or with the second last term. Let's see here, it will be what? 10, 18. Are 10, 18 in the same group? Yes, okay. So because of this, let's see also for 58. Can we say 58 is bad? No. 50. What about 50? No. Okay, why we said here? Let's check for 2. 22. Why was bad? Because we've selected here. Let's see what are the numbers we've selected in previous case. No, we don't see anything like that. It's because there are 61, 71, 81. And also here 36. Okay, so if we consider 58, 50, none of them, our modulo 10 is 1. So here we can consider what we've rejected contradiction because of these two terms and 1. So we've reached contradiction. Now we proved why 9 is bad. Let's consider now n equal to ak for solving next problem. And for general A, we want to reject AK. So by here, if we reject this, we prove that composite numbers are bad. Then we should focus on prime numbers. Okay, suppose n is AK. And again, we want to say last A rows. The common difference for last A rows should be A, and for other rows it should be 1. So we write 1, 2 to n, okay? Or let's write AK plus 1 to 2AK, AK plus 1, AK plus 2, the next one 2AK plus 1, 2AK plus 2, 3AK, and so on, up to, let's consider the last A rows. Here, we should consider what? We should consider n minus, it is for 1, 2, 3. This one is n minus A, okay? Because we have A rows. So AK minus A, and then it is AK minus A plus 1. Let's consider AK minus A plus 2, and suppose we have for some rows here, and this word will be AK. Now, let's consider other elements here, all of them AK minus 1, 2AK minus 1, 3AK minus 1, and then for this word AK minus A also satisfies this, all of them the common difference 1, 2, 2, this one AK minus 1 also on. Sorry, the common difference here, let me consider the common difference 1, 1, 1, and also for this one it is 1, for this one it is A, this one A, and this one A. Okay, suppose we have for example some rows here. Now AK minus A. As you can see, 1AK plus 1A, 2AK plus 1, because it is 2, 1, it's 3, 2. So it will be AK minus A minus 1 times AK plus 1. And then the next one is the same thing, AK minus A minus 1 times AK plus 2. And also we can write let's write instead of AKN, okay? Because we know n is AK, then we have more space. So it is what? It is n minus A, it is n minus A plus 1, it is n minus A plus 2, and the last row is n. So here when we want to multiply, we say, okay, it is n minus A, so we can write what? N minus A minus 1 times K plus 1. Okay, let's see. 2 times, so, times n plus 1. So it is n plus 1, 2n plus 1, n minus A minus 1 times n plus 1. The next one will be n minus A minus 1 times n plus 2. And this one will be what? N, 2n, 3n, n minus A times n minus A times n plus 1, minus 1. And now here, it will be n minus A times n plus 1. Okay, the first one after that. And the next one will be what? N minus A times n plus 2. And then the last one is what? N minus A times n. So here, look, first row, second row, eighth row will be plus A. And then we add by what here? We add by A. The common difference is A. So it is n minus A times n plus A plus 1. Or let's write like this, plus 1 plus A. The next one, n minus A times n plus 2 plus A. N minus A times n plus A plus A. And so on. Up to, let's consider these last three terms. We said we have a formula. An is A1 plus n minus 1 times d in arithmetic progression. Is so much important. So here, when you consider this one, if we want to find last term, you say, okay, the first term is n minus A times n plus 1 plus n minus 1 times d. D is what? A. So we have n squared minus an plus 1 plus na minus a. This will be cancelled, so n squared minus a plus 1. N squared minus a plus 1. And also, the second term, as you can see, each term is plus one of previous terms, so it will be n squared minus a plus 2. And this one will be n squared minus 2a plus 1. This one will be n squared minus 2a plus 2. And because we have dot, 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 the last term here, it should be n squared. Let's see, to not have any careless mistake. This one will be what? The first term, n minus a times n plus n minus 1 times the common difference a. So it will be n squared minus na plus na minus a. It will be cancelled, and it will be n squared. So it will be n squared minus a. Okay, so we found all terms in our cells. So let me erase this part. Again, we want to use same method. We say, okay, after 1, the next term can be what? Here, it is n plus 1. Instead of ak plus 1, you can say n plus 1 also. It can be n plus 1, or it can be n plus 2, because 1 to n are in first row. So it is plus n, the next one 2n plus 1, and the nth term will be what? an equal to 1 plus n minus 1 times d. d is what? d is n. So it will be what? So it will be n squared minus n plus 1. Okay? The previous term is n squared minus 2n plus 1. And now if we consider here plus n plus 1, it will be 2n plus 3. And the last term will be what? Will be first term plus nth term is n minus 1 times common difference n plus 1. So it will be 1 plus n squared minus 1, which will be n squared. So here it's n squared, the previous one is n squared minus n minus 1. And as you can see, we have only these two cases, because if you consider another one, the last term will be greater than n squared, and we have only 1 to n squared. Now, like previous ones, we rejected first case. How we rejected first case? Because of these two elements. We said n plus 1 and 2n plus 1 are in same row. It is n plus 1, it is, let's see, n plus 1, 2n plus 1. No, it is 2n. So let's see how we rejected first case. 713. No. So let's see, 1925. We rejected with 2531. Last two cases. Okay. So here, like here, last two cases. So we should prove that these two things are in same row. N squared minus n plus 1. Now, if we consider n squared minus 2n plus 1, n squared minus an plus 1. So, as you can see, for example, we said in 9. If we consider 64, 73, last two terms are in this row. In first row that we have 3. Here also we want to prove same thing. We want to prove that they are in this row. The reason is what? The reason is this. These two numbers are what? Here, because we have plus a, when we have plus a, all n, for example, n minus a times n plus 1. If we consider mod a, we know that because n is multiple of a, it is 0, 0, 0, it is 1. Okay. And these two numbers are also mod a, because n is 0, are 1. So the remainders are exactly same. And because here we have plus a between first number and last number, we cover all numbers that mod a are 1. Okay. So the only thing we should prove that these two numbers are between these numbers. So we should prove that n squared minus 2n plus 1 and n squared minus n plus 1 are greater than equal first number n minus a times n plus 1 less than or equal last number n squared minus a plus 1. Okay. Because we know that this number is less than this number, because it is plus n, so we should only prove this is greater than equal this and this is greater than equal this. This one is equivalent to what? N squared minus na plus 1, why it is less than or equal n squared minus 2n plus 1. We can cancel n squared, we can cancel 1 from both sides. We can divide both sides by n and take -2 to left hand side and a to right hand side. So a is greater than or equal to, yes, because we said a is composite number. And also we prove for a too, but this proof, look, you don't need to write all these things 2k and 3k like this. You only need to start from here. Okay, here n is a composite number, a and k are at least 2. Okay, so this part is correct. Now let's prove this part. We should prove y n squared minus n plus 1 is less than or equal n squared minus a plus 1. We cancel n squared from both sides. We cancel 1 from both sides. We take -a to left hand side, -n to right hand side, and it is correct. Why? Because we know that n is ak. Also, we know that n is strictly greater than a. And here, like previous cases, we rejected this, so we have 1n plus 2 and 2n plus 3. This. Now we want to consider 2. For 2, we should consider 2 situations and reject for both of them. Let's consider 2. Because 1 to n are in same row, in first row, the next one after 2 can be n plus 1. Like this one, let's check to 10. Yes, n here was 9. To 11 was not possible. Also to n plus 2 is not possible because we have n plus 2 here. So the next one is 2n plus 3. For this case, we also for this part, for 9, and also other cases, we said that we reach a number greater than n squared. Here, let's see, it is plus n plus 1. Here, the next one is 2n plus 4. And if we want to consider nth term, again, we use same formula. an is a1 plus n minus 1d. You say a1 plus n minus 1 times common difference n plus 1. So it will be 2 plus n squared minus 1, which is n squared plus 1. Okay? So this part is bad. If you consider this one, it is plus n minus 1. So plus n minus 1 is 2n, plus n minus 1 is 3n minus 1. And if you want to consider last term, it will be 2 plus common difference n minus 1 times last term n minus 1. It will be 2 plus n squared minus 2n plus 1. So it will be n squared minus 2n plus 3. And let's consider something. How we rejected? We rejected because of first two terms. Also, we don't need to continue this. We can also write this n squared minus 2n plus 3, but we don't need to write this because of n plus 1 and 2n. They are in first, second row, n plus 1, 2n. So both cases are impossible and we don't have any other cases. So we reach contradiction like 2k, 3k. Okay, so this part is proof of the case that why composite numbers are not okay. You need to only write this part for rejecting composite numbers. We found an example, and how we found this example? By considering a small example. Now let's focus on prime numbers. Suppose n is p, which p is prime. Now, if we consider, for example, a1, then a1 plus t, d, a1 plus 2d, for some common difference in a row is d. Our arithmetic progression will be a1 plus n minus 1d. And then we can conclude what? We can say we have two cases. Case 1, d mod p is 0. Then if we consider these elements, mod p, the remainder of all of them mod p will be a1. Okay, so it means that we have all of them are a1. But this thing R is mod p, our sequence. Case 2. If d is not 0 mod p, then I want to say we have how many numbers? N numbers or p numbers. Okay, let's consider instead of n we write p minus 1. I want to say these p numbers, the remainder of these p numbers when divided by p are different. So we have 0, 1 to p minus 1. The reason is what? Suppose, for example, a1 plus id is congruent to a1 plus jd mod p. I want to say All of them have different remainders when divided by p. Suppose two of them are different, so we subtract a1 from both sides and we divide by d. When we divide by d, you should consider by the rule in modulo, you should say divided by GCD of p and d. We know GCD of p and d is 1 because d is not 0 mod p and p is prime. So I is congruent to j mod p. But we know the coefficient id is from 0 to p minus 1. So I and j are from 0 to p minus 1. So I and j, because the remainder when divided by p equals, so I equal to j. So if we select two different numbers here, their I and j are different, so they cannot be congruent mod p. And then we conclude this sequence mod p will be 0, 1, 2 to p minus 1 in some order. Okay? Now, let's consider, let me tell you, for example, for prime number 5, okay? Then you understand completely. You say how many zeros are there? 0, 0, 5 zeros, 5 ones, 5 twos, 5 threes. Our table is not this. I want to just write the remainders. 4, 4, 4, 4, 4. So 5 zeros, I mean, they are what numbers? 5, 25, 5, sorry, let's write in order. 5, 10, 15, 20, 25. And for example, next one is 1, 6, 11, 16, 21, and so on. And last one is what? Is 4, is 9, is 14, 19, 24. So we have these numbers. And now, we've proved here that if we consider each row, all of them have same remainder, or all of them have different remainders, 0 to p minus 1, or all of them same. So I want to say both cases cannot happen simultaneously in a table. Why? Because look, if you want to select, for example, in one row, all different remainders, 1, 2, 3, 4, then you can select, for example, for one of them 5 zeros, because 1 0 was removed here. We've selected 1 0 here, so 4 zeros are left. So we have two options. If we consider it is our table, okay? Okay, the first table is we have all the remainders in each row, 0, 1, 2, 3, 4. Again, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And our second table in some order. Our second table is what? We have 4, 5 zeros, in for example, without loss of generality. In first row, the orders of rows are not important. 5 ones in second one, 5 twos, 5 threes, and 5 fours, okay? Now here, we should select these 5 zeros, means permute each row such that the red cells be on first column. Then you select OK. These ones you permute such that the green cells be in second column. For example, you permute such that the pink one be in third column. You permute such that the black cells, or the threes, be in fourth column and the fours be in last column. Next one, you say, okay, all zeros are in first row, all ones in this one. So because of this, we conclude what? We conclude our table here will be what? Will be, the first one is 5, 10. Let's consider, let me draw a table. Okay, because we have all zeros here, it will be what? 5, 10, and on. Why these reds are good here? Because they are 5, 10 to 25. They are arithmetic progression. In this case, the rows are what? The first row 5 without loss of generality. The first rows are zeros. 5, 10, 15, 20, 25. The next one is 6, 11, 16, 21, 26, 20, sorry. 6, 11, 16. And we should start from 1. Okay, so this one will be what? 1, 6, 11, 16, 21. This one will be 7, 12, 17, 22. The next one is 3, 8, 13, 18, 23. The last one is 4, 9, 14, 19, 24. Okay, now in this case, we consider 1, 2, 3, 4, 5, okay? And because all of them have different remainders, they are from different rows, okay? We consider all numbers that are from 1 to 5 to first row. And we can also say if we sort each row from increasing in increasing order, so first row is okay because we have 1 to 5, second row is okay because we have 6 to 10. The common difference is 1 for each column. 11 to 15, the next one 16 to 20, and the last one is 21 to 25. So we can say exactly same proof for P. Let me say for prime number. For general prime number, you say we have two cases. Case 1, we have zeros on, for example, we have all remainders in each row. So we have 0, 1, 2 to p minus 1, 0, 1, 2 to p minus 1. Okay, so you permute each row such that the zeros be in first column, 1 in second column, 2 in third column, and p minus 1 in last column. So we do this, and it is case 1 that each row has all remainders. And as you can see, it will be good because each column has all multiples of p. So for example, the first column will be what? In some order. It will be p, 2p, 2p squared, which common difference is p. This one will be what? 1p plus 1, 2, and the remainder is 1p squared minus p plus 1. And if we consider k, it will be what? K, p plus k, 2p squared minus p plus k. There are p numbers, and the remainder, the common difference of these numbers are p. Case 2 is the case that in each row the remainders are same. Means here you have, for example, 0, 0, 0, 0, 0, all zeros in first row. And because it is all of them are zeros, so you say, okay, I consider from in increase, I permute. The problem says we can permute each row, so you consider p to p in increasing order, 3p to p squared. Then for 1, you permute, all of them are 1, the remainder when divided by p. So we consider 1p plus 1, 2p plus 1, and p squared minus p plus 1. The next one is 2, p plus 2, 2p plus 2, and p squared minus p plus 2. And the last one is p minus 1. You say plus p, 2p minus 1, 3p minus 1, and the last one is p squared minus p plus p minus 1 or p squared minus 1. Okay, and first row is good because 1 to p, the common difference is 1. Second row, p plus 1 to 2p, and for example, kth row is kp, kp plus 1, kp plus 2, 2kp plus p minus 1. And here our numbers are what? Or let me, sorry. Let me write it again. Then it is, let's consider first one is, for example, k plus 1 times p. Then, if you consider, look, each column, it is p minus 1 less than this, p minus 1 less than this. So if you subtract by p minus 1, or you can also use arithmetic sequence, it is first row, second row, k plus first row, and it will be kp plus 1, kp plus 2, kp, here it will be kp plus p minus 1 or k plus 1p minus 1. And if you consider starting from here, It will be all numbers up to this one and last one here. Common difference is 1, and last part also you start from this part, this. Last one will be p squared. So in both cases we proved that for all prime numbers it is good. So now let me write some homeworks for you to solve with this method. Okay, you can solve this IMO problem with this idea as homework number 1. There are also 2 other homeworks from BMO, British Mathematical Olympiad, round 2, 2023, homework number 2 and 3. Question number 2 and question number 3. Let me paste them. Okay, this problem is question number 2. BMO is for British Mathematical Olympiad. Question number 3. Okay, this homework number 3. You can solve these problems with again considering small examples, and there are lots of other problems with these ideas. So I can say the most useful idea for approaching a problem is considering small example, and we have also lots of other ideas, like for example recursive sequence, a famous question you should ask, an important question. I can say it's not famous because there are few students know. And in each topic, for example, when we have lines, we should do what when we are working with regions. If you want to learn important ideas in combinatorics, also we have same ideas in other topics, geometry, number theory, and algebra functions. If you want to learn those ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. Okay. Last problem of USAMO 2023, problem number 6. In this problem, we should work with x-centers. And after solving this problem, I will leave a problem as homework IMO problem. In that problem also we have IA, IB, IC, and that problem is similar. Similar things you should use, and it's useful for getting good at, for example, when we have x-centers, in-center, and so on. Okay. So let's read the problem. Let ABC be a triangle with in-center I and x-centers IA, IB, IC. Opposite AB and C respectively. Let me show you the figure is what. Look, for example, it is ABC, this IB, IC, and this part IA. Let me minimize a little. The figure will be like this. Okay. So let's read the rest. Let's maximize. It says let D be an arbitrary point on the circumcircle of ABC that doesn't lie on any of the lines IA, IIA, IB, IC. So these here. Okay, the on circumcircle doesn't lie on I. It is I on IIA. And let me tell you. Oh, sorry. I is not here. I is the intersection of internal angle. Oh, sorry. I is exactly this one. Okay. I is here. Let's read the rest of the problem. It says arbitrary point that doesn't. Okay. Or BC. Suppose the circumcircle of DIIA and DIBIC intersect at 2 points D and F. Okay. DII, let me minimize. DI, let me select this. DIIA, this pink circle, and this pink circle passes through DICIB. They intersect at D and F. Okay? Then the problem says what? The problem says if E is the intersection of lines DF and BC, it is E, then prove that BAD equal to EAC. BAD is what? BAD, let me draw. Let's select brown. Okay. BAD is this angle. I show it with 1 point. And EAC is this angle. Again, I show it with 1 point. We want to prove these two angles are equal. So, And the way I want to approach this problem, I define another point E prime and I want to prove it is E. Exactly one problem of, let me tell you, BMO 23, 22, 2021, British Mathematical Olympiad round 2. Could be solved with the same idea. For example, in that problem, if you want to prove AK something 90, you define another K prime and prove K equal to K prime. Let me just copy and paste the problem that is useful with a similar idea that you can solve it after this video as homework. Okay, let me write as homework number 1, PMO round 2, 2021, this problem. And after solving this problem, I will leave another homework number 2. It's IMO problem. It's related to excenters. Let's solve our problem. Okay, here I want to prove what. Okay, I want to prove. Look, this is what we call it radical axis. When we have two circles that their intersection, we call this line radical axis. So the problem says E lies on radical axis. Prove that this angle equal to this angle. I want to define some other thing. I say, suppose E prime is a point that this angle equal this angle, then I want to prove E prime lies on this radical axis. It is equivalent to the problem. The BMO problem is exactly the same idea. This way is so much famous in geometry, an important good approach. So these two angles are equal. We want to prove E prime lies on radical axis. And now in some problems like this, that the problem is not easy, you should work a little on sentence of the problem, a little on assumption of the problem. But before solving this problem, I should tell you some basic things. As I told you in my previous videos, there are around 40-50 important formulas in geometry. Here we want to use some of them. So before solving the problem, I should cover them and then we can focus on this problem. Okay. The first thing you should know is in any triangle, let's consider it's at lemma 1, AI times AIA equal to BC equal to AIB times, let's call with excenters, IA with big A, we can say small a. Okay, so let's write with a small a like the problem. We can use both of them. AIA, AIB times AIC. And before that, let me just tell you the 4 conditions in cyclic quadrilateral. It is a lesson, it's not something to prove. The proofs are easy. If you had question, we have 4 rules for cyclic quadrilaterals. You should know them in all exams from basic level, from M.Sc up to IMO. They are so much useful in all the years. So the first thing is what is that if you have a cyclic quadrilateral, opposite angles or sum of opposite angles equal 180, the 2 of them related to angles, 2 of them related to lengths. This one and the last one is this one, this one. Okay, let's consider. For first condition, second condition, let's consider third condition, fourth condition. A, B, C, D, A, B, C, D, there are diagonals. Here A, B, C, D, and the intersection is P. This word, let's call this P. Extension, the intersections of the opposite sides that intersect in P. So in each of them, we want to see ABCD is cyclic if and only if what. So first condition, we have also another rules, but these rules are the most basic rules. Okay. The first one is A plus C equal to 180, sum of opposite sides equal to 180, if and only if ABCD is cyclic. Okay, so let's write also like this. If and only if ABCD is cyclic. If it is cyclic, it is obvious because it's sum of this arc plus this arc, 360 over 2, 180. If it is a sum of them 180, then you should use in the contradiction to prove it is cyclic. The next one, A1 equal to B1, then ABCD is cyclic if and only if. The next one, ABCD is cyclic if and only AP times PC equal to BP times PD. Then ABCD is cyclic. Last basic condition is PA. Look, this one, PA times PC equal to PB times PD. This one, PA times PB equal to PB times PC. So we consider it is PA PD equal to PB PC if and only if ABCD is cyclic. I will prove one from first one, one from second. Let me tell you, I prove this one, and then, and also one of them. For example, second one and fourth one. First and third one you can prove by yourself. For this one, the proof is what? If it is cyclic, A1, B1 see the same arc. So from bottom to top, it's obvious. From top to bottom, you say, okay, A1 is B1, we want to prove ABCD is cyclic. Let's use contradiction, okay? So, suppose it's not cyclic quadrilateral, okay? Control V. And then you draw a circle through 3 points here. For all of them, we use same proof. Let's consider the circle passes through A, for example. D, and okay, so let's consider it passes through this point, this point, this point. Okay, now you extend, let's consider also B, for example, a little more inside or more outside to be able to create something like this. Okay, B is here. Now we extend this. So it is B prime. It is B1. We know B prime, this angle. See the same arc, and A1 see the same arc. So we know A1 from assumption equal to B1, and A1 because they see same arc equal to B prime. So we can conclude angle B1 equal to angle B prime. But if we consider this one as, for example, C1, we know B1 is exterior angle of BB prime C. So B1 equal to B prime plus C1, which means that B1 is greater than B prime, so that's a contradiction. For fourth rule, let's prove it. You can prove first and third by yourself. If ABCD is cyclic, we want to prove this. So let's draw a figure like this. You have this one, this one, this one. We use similarity. This one. And it is P, it is A, it is B, it is C, it is D. We know this angle equal to this angle. Why? Because A plus C 180, A plus this angle 180. Why this one? A1 plus C is 180 because of first rule. And that you should prove by yourself as homework. This one plus this one 180. A1 plus this one 180, so these two things are equal. Similarly, these two things are equal. So we can conclude triangle PAB is similar to triangle PCD. And then PA is opposite to this one. And here it is corresponding to PC. PB opposite to this PD. And if we cross multiply, then we can conclude PA times PD equal to PB times PC, which was exactly the thing we wanted to prove. Now if we want to prove that we have this equation, we want to prove ABCD is cyclic, okay? If we want to prove this part, we use again contradiction. Suppose ABCD is not cyclic, and we have this relationship, okay? We have this relationship, and ABCD is not cyclic. Again, I draw a circle that passes through three of them. So let me, before that, say it is P, it is A, B, for example, C, D, PA times PB equal to PA times PD equal PB times PC. We want to prove why ABCD is cyclic. Now we draw again a circle that passes through three of them. For example, like passes through a BDC or also ADC. Now because of previous part that we proved, let's call this part star, that we proved by a star, we consider this one A prime. By a star, A prime, we know A prime BCD is cyclic. So if we use a star, PA prime times PD equal to PB times PC. And also by assumption of the problem, we know PAPD equal to PBPC, and all terms are equal except PA prime, so PA equal to PA prime. And that's a contradiction because then A equal to A prime and ABCD was cyclic, but we've used contradiction. That we said they are not cyclic. ABCD are not cyclic. Is not cyclic, quadrilateral. Okay, so I've told you these things. Do prove this one as homework number. Homework. It's not number that and homework. Okay. Now I want to prove that y AIAIA equal to BC equal to AIB AIC. So let's show it here. So in this figure, we draw ABC, for example, like this. And then we want to draw. At first, I prove AIAIA equal BC. Okay, so 2, 5, 4, 46, 56, 60. So 32, 8, 4, 5, 4, 2, 8, 4. Around this, and now let's also extend, for example, this one to find this. Okay, so at first let's draw this 360, 74, 37. Okay, now 37, 53, 53, 310, 37. Okay, AI is this. Now I say it is B, it is C, it is ABC, it is IA, it is I. Now for proving this part, I draw these two lines. I want to prove similar triangles. At first I want to prove it. So now by this line you can find two similar triangles and prove this by yourself. So pause the video and try to prove this by yourself. Look, this angle is what? A over 2. This angle is what? A over 2. This angle is what? C over 2. And let me tell you something. This is what? A plus C. Okay, because it is exterior angle. And it is external angle bisector. So A plus C over 2. So we conclude that this part is A over 2 plus C over 2. Now, this angle is exterior angle of this. It's A over 2 plus C over 2. We have A over 2, so it will be what? It will be C over 2. Now, as you can see, we can say by two angles, triangle ABIA is similar to triangle AIC. So we can say in ABIA, let's consider C is B. C over in AICC is opposite to C over 2, C over 2 AI. Equal to, in AIC, we consider B, B is opposite to this one, AIA. Okay, so let's consider also use I small a. Now if we cross multiply AI times AIA equal to BC. Okay, so we proved this part. Now I want to prove this part. Okay, so let me copy this one again. I want to use, let me tell you. I want to use again similar triangles. At first angle chasing, then similar triangles. So let's extend them. Let's extend this one. Let's extend, okay, up to this point and this. So let's erase the things that we don't need. Yeah, I think this part we don't need. And we only need this part. The other things are not important. Not important, not important. Okay. This part. It is IC, it is IB. Now let's use a little angle chasing. I know that if I consider with blue, let's extend this. I know that this angle is what? It is A. It is 180 minus A. Okay, 180 minus A. So because it is external angle bisector, you say, okay, it is 90 minus A over 2. And also we can write only for this part we need 90 minus A over 2. Both of them equal to this. Both of them equal to this. Similarly, you say, okay, if we extend, for example, this line, it is C, it is 180 minus C because it is a straight angle. Half of that when we draw external angle bisector, 180 minus C over 2 is 90 minus C over 2. Now I want to find this angle. I say, okay, it is 180 minus the sum of these two angles, 90 minus A over 2 plus 90 minus C over 2. So it will be 180 minus 90 minus 90 minus 180 plus A over 2 plus C over 2. We cancel. We know A plus B plus C, sum of angles of triangle ABC equal to what? 180. So half of that equal to what? A over 2 plus B over 2 plus C over 2. equal to 90. So we conclude A over 2 plus C over 2 is 90 minus B over 2. Okay? So we write this 90 minus B over 2. Similarly, again, you say same thing for here. You say, okay, if we extend this part and extend this part, it is 180 minus A, so it is 90 minus A over 2. This part is also 90 minus B over 2. And with the same proof like this, similarly, this part is 90 minus what over 2? 90 minus C over 2. And as you can see, these angles here and here are equal by two angles criteria. You can say ABIC. Let's write triangle symbol. ABIC is similar to ACIB. And then C, if we write C, corresponds to 90 minus C over 2, 90 minus C over 2, AIB. And in this triangle, if you write B, B is opposite 90 minus B over 2, 90 minus B over 2, AIC. And if we cross multiply AIB times AIC equal to BC. Okay. So we proved also this part. Now for next part, I want to tell you power of a point with respect to circle and linearity property in that. And the thing here we want to use, so let me explain for you. Suppose we have a point P. Power, for example, is omega. Then power of this point, power of, for example, P with respect to omega equal to PO squared minus R squared. Okay. So, for example, we have this PO squared. If we draw common tangent to this part, we can say, okay, this is PO squared. It is K. So, because we know this angle is 90 degree, it is the definition, okay? Definition of power of point with to this circle. It is definition. And then we can prove what? One thing. We can say, okay, PO squared minus R squared by Pythagorean theorem. We can prove power of point to circle omega equal to PK squared. Right? Why? Because PO squared minus R squared equal to PK squared. And also another thing that we can say that if you have a point here, for example, P, if it is A, it is B, we know that PK squared equal to PA times PB. You can prove it by similar triangles. PAK is similar to PKB. You can prove this. So it is power of a point when it is outside. When it lies on the circle, so it is positive when it is outside. When it lies on the circle, power of here, power of, and suppose it is omega, power of P with respect to omega equal to 0, okay, because P and K are same. Or if you use PO squared minus R squared is 0 by the definition, because PO is R. So if you write PO squared minus R squared is R squared minus R squared, which is 0. Now the last part, when P is inside. So we consider this. For example, P is here, O is here. So power of, again, point P with respect to W is PO squared minus R squared. And here it's negative because PO is less than R. Now we can say something. We can say, okay, PO squared minus R squared. We can say it is PO minus, let's consider this AB. It is PO minus R by algebraic factorizing. Difference of perfect square, PO minus R, difference, subtraction times sum, PO plus R, PO minus R, let's consider, I consider negative of that, okay? So let's consider negative, it will be what? It will be minus plus, so it will be negative of R minus PO is what? Is PA. PO plus R is what? PB, okay?
So we can say PA times PB is negative of the power of the point. Okay, and let me tell you something. You can also say you can draw P to, for example, another point PCD. Also, we can say PC times PD for any point. Like this, we know it is also equal to negative PC times PD. It was a property in cyclic quadrilateral I told you here. Okay, so it will be negative of PCPD or PAPB. They are equal to negative of the power of point omega or power of point P to the circle omega. Okay, we've considered this. Now I want to tell you something. Okay, so let me tell you lemma 2, lemma 3, lemma 4. Lemma 1 was what was this one? And then I told you the definition here. Let me tell you lemma 2, lemma 3 are not hard, and then lemma 4 we prove. Lemma 2 is this, that we have two circles, then we have this one, we draw two lines like this, call this one P, call this one M, call this one N, call this one A, B, C, D. We want to prove ABCD is cyclic, and we call MN radical axis, okay? And always in some problem when you don't have radical axis, it's good to draw. In many problems it's useful. So draw always radical axis. So much useful. If it is not drawn also, try to draw it. Okay, let's prove it. We know AMND is cyclic. So we can say PA times PD equal PM times PN. By what rule? By fourth rule of cyclic quadrilateral. By this one. Okay, because ABCD is cyclic, PAPD equal PBPC. So here we can say PAPD equal to PMPN. Why? Because AM and D is cyclic. Now PMPN equal to PBPC. So why? Because MBCN is cyclic. And because these two things are equal, so we conclude PAPD equal PBPC. And then we can say ABCD is cyclic. Okay, this part is important. Why? Because you understand why. You understand what? You understand that. Because P lies on radical axis, the power of point with respect to these two circles are equal. It is important point. And P was outside. In lemma 3, we want to consider the case that P is inside. Okay, let's write lemma 4. Lemma 3. Lemma 3. In this case, we have again two circles. But here, instead of the case that P is outside the circles, in this case, P is inside the circles, okay? And then, again, it is, for example, MN. It is AB, CD. P is inside circles. Okay, so we want to prove ABCD is cyclic in this lemma. Prove that. Okay, prove that. Also in previous one, we wanted to prove that. Also in lemma 1, prove that. Okay. So let's prove this part. Again, similar to previous proofs. Again, AP times PC equal MP times PN. Because AMCN is cyclic. So AP times PC equal to MP times PN. Why? Because AMCN is cyclic. and MPPN equal to BPPD. Why? Because MPND is cyclic. MBND is cyclic. Yes, BPPD. So we conclude first term equal to last term, AP times PC equal to BP times PD. And by third rule, I told you for cyclic quadrilateral here that you should prove it as homework. We conclude ABCD is cyclic, okay? Okay, now in lemma 4, I want to use linearity of power of a point. Let me tell you, I will prove the thing that we need here. Suppose, again, we have two circles like this, and then we have, this is our radical axis again. Let's draw this. Let's draw this, and then we draw a perpendicular to this radical axis here. It is not needed to say we draw a perpendicular. Look, let me tell you, it's 153, 236. Okay, will be some point like this. Now suppose it is P, it is Q, and consider it is M, it's midpoint. And for example, let's suppose it is K, it is L, and then suppose it is omega 1, it is omega 2, PM equal to QM. Prove that power of. Okay, we can write P or POW, power of point P with respect to circle omega 1, minus power of P with respect to omega 2, plus power of Q with respect to omega 1 minus power of Q with respect to omega 2 equal to 0. Okay, let's prove it. I want to prove with green. I consider this point as A. This let's consider in order. It is A, it is B, it is C, it is D. Okay, so power of P with respect to omega 1 is what you say it's PA times PC. We proved in previous part. Let me tell you. Here. PA times PB is power of P to omega. Now here it is PA times PC minus power of P with respect to omega 2 is PB times PD. We want to prove why it is 0. Power of Q to omega 1. Omega 1 is first circle. Is QC times QA. And power of Q to omega 2 is QD times QB. We want to prove why it is equal to 0. Now I want to write it in terms of, because we know PM and QM are equal. I say, okay, PA is what? Is PM minus MA. The first one, PA is PM minus MA times PC is what? Is PM plus MC minus PB is what? Is PM, look, PB is PM minus MB. PD is what? Is PM plus MD. Plus, let me move it to left. Plus QC is what? Is QM minus MC. QA is what? QM plus MA. Minus QD is what? Is QM minus MD. And QB is what? QM plus MB. Equal to 0. We want to prove why it is equal to 0. Now, if we expand, let's expand. The first one is PM squared plus PM. Let's factor from PM. PM times MC minus MA minus MA times MC. Here, minus PM squared. Then we factor from PM minus plus PM times MB. It will be MB minus PM times MD. We have minus MD. Minus plus MB times MD. Now plus. We write this in second row. QM squared. Again, we factor from QM. MA minus MC. Minus MA times MC. Minus QM squared. Plus QM times minus plus MDQM. It's MD. Minus QM times MB minus MB. Minus plus MB times MD. We want to prove why it is equal to 0. Okay, so we cancel PM squared, negative PM squared. Now we factor from PM. It will be MC plus MB minus MA minus MD. Then we have negative MAMC, two of them, 2 MAMC. This part 2 MB and D plus QM. If you factor from QM, again QM squared will be cancelled. QM squared and negative QM squared here. If you factor from QM, it will be MA plus MD minus MC minus MB. We want to prove why it is 0. MAMC MB. Look, MA MC equal to, let me write the other with pink, MD. It is negative of power of point M with respect to these two circles, but we know M lies on radical axis, so we know MKML equal to each of them. So we can say what? We can say MC. It is exactly like the thing here we've used in lemma 3. Okay? In lemma 3, we've used same thing. MPMN equal PB, PD, PA, PC. So it helps us to understand here easily. MC times MA equal to MK times ML equal to, let me tell you, MA, MC, MK, ML, MB, MD. Okay, so MC, MA equal MB, MD. So MA, MC, MB, MD, it's 2, negative 2. Now the last part, we should prove why it is equal. And as you can see, we can write it as MC plus MB minus MA minus MD. Here you write PM. And this part, if for example it is T, you can see easily that it is negative T. Okay? All signs are different. Now here, it will be PM, it is T, minus QM. And we know PM equal to QM from assumption of the problem. M was midpoint of PQ, so it is 0. Okay, because this part is 0. So it was lemma 4. Now we are ready. Before solving this, let me tell you one more lemma. Lemma 5. That it says BICIA is cyclic. Prove that. This. So we had we don't need to draw the graph again. We have this. Let's prove why it is cyclic. So here, look, if we draw this part, we can say Let me erase the things that we don't need. We don't need any of these things. You can use them, but we don't need them. Okay, this is now. Look, we know that it is internal angle bisector, external angle bisector. Sum of them is what? 180. So now we draw two angle bisectors, internal, external. So half of this plus half of this, half of 180 is 90 degrees. So it is 90. Similarly, it is 90. It is a rule. Internal angle bisector is perpendicular to external angle bisector of an angle. So here B, C, both of them are 90. So we can say, okay, B plus C equal to 180. Sum of opposite angles equal to 180. By the first rule in cyclic quadrilaterals, we can say BICIA is cyclic. Let me tell you lemma 6. It says IC, IB, CB is cyclic. Let me also prove this part for you. Look, we've used angle chasing here. We can use angle chasing copy that we've done in that lemma. Okay, so this point, this point, this point, this point. It is B. So if we consider this angle plus this angle, we want to prove that sum is 180. Sum of them is what? 90 minus B over 2 plus B plus 90 minus B over 2. Which is negative B over 2, negative B over 2, negative B by B, 180. So ABCD is cyclic. So IC, IB, CB is cyclic. Also, you could say some easier thing. We know it is 90 minus B over 2. It is 90 minus B over 2. This one equal to this one. So this one equal to this one is equivalent that this plus this is 180. So it is cyclic. So lemma 6. Now I think we are ready to solve the problem. Okay. Let's go back to our figure that we had. Okay, this figure. I consider here E prime is what? E prime is a point at this angle equal this angle, and now we want to prove that E prime lies on DF. It means that what? Lies on radical axis. So we should prove power of E prime with respect to this circle equal to power of E prime with respect to this circle. Okay, let's consider this one omega 1, this one omega 2. Now we should prove, let me open a new page. We should prove, we want to prove E prime equal to E. So it is equivalent that we prove power of point E prime to omega 1 equal to power of E prime to omega 2. So let's see how can we prove this. Here, at first, in problems of AMC, AME, always similar triangles are so much useful. Here, if we connect this to this one, you can see that, let me tell you, here we said that A plus C 180, it is equivalent that when we have cyclic quadrilateral, this angle equal this angle, because we know A, this one plus this is 180. So these two things equal means that it is cyclic quadrilateral, or if it is cyclic quadrilateral, these two angles are equal. Now because of this, we will see that this angle equal to this angle, okay, ADB. Now because of two angles, it is this, it is this, it is this, it is 180 minus C. So we conclude what? Let me write here and then I will paste a new page. By two angles, triangle ADB is similar to triangle ACE prime. And then we can say AD corresponds to what? To this angle that here, this angle, it's AC, which is B. And here, if we consider C, then it is what? C here, this angle, AE prime. Okay, so let's copy and paste here in our new page. Okay, so by two angles, we prove this, and then we prove this, and then it's a good thing. Why? Because we proved AE prime equal to BC. And we said what? In lemma, let me tell you 1. We said AIA equal BC equal AIC. So we can use it, and we can say, okay, AE prime, which is equal to BC, equal to AI times AIA, equal to AIB times AIC. Okay? Now let's work a little on angles. We want to use a little angle chasing. We know it is A over 2 because it is internal angle bisector. It is A over 2. And suppose this point, let me maximize to write alpha here, alpha here. Now let's work on the other angles. If I extend AB, I want to see our angle is what? We know that because it is, and one more. Let's see if we needed that. I will tell you. Look, the circumcircle of ABC is 9-point circle of IAIBIC. The reason is what? Because this is 90-degree internal external angle bisector. So ABC are feet of altitudes from IAIBIC. So ABC is orthic triangle of IAIBIC. So we know that 9-point circle passes through feet of altitudes, and another thing, midpoint of sides here, midpoint of IAIB, IBIC. So that's the reason that I say, for example, here is MA, MC, MB. It's midpoint, and also it passes through midpoints of, for example, in general, if for ABC we draw 9-point circle, AH, BH, CH. Okay. Now let's consider something. If we draw this circle, extend this line, it is alpha A over 2, A over 2. We know the whole angle here is what? Because it is A over 2, we know it is 90 external angle bisector, or it is 180 minus A, so we know it is 90 minus A over 2. Because it is alpha, this part is 90 minus A over 2 minus alpha. And now, if we want to find this angle, it will be what? Let's see this line. If we focus on AB, it is A over 2, A over 2, alpha 90 minus A over 2. So here we can say, because it is, we can say external angle bisector 90 minus A over 2. But if we extend the brown line, means what? Means this one. We will create exactly the same angle. Look, if I extend this one, here we have alpha plus A over 2 plus A over 2 plus this one. Let me write here. Alpha plus A over 2 plus A over 2 plus alpha plus 90 minus A over 2 minus alpha. This one will be cancelled, A over 2 will be cancelled, so it will be alpha plus A over 2 plus 90. So if I want to write the part that is left, the sum should be 180. So 180 minus 90 plus alpha plus A over 2. 180 minus 90 is 90 minus alpha minus A over 2. So we conclude that this angle also equal to 90 minus A over 2 minus alpha. And that is so much good because these two angles are equal. So let me erase the things I wrote here for finding that angle. Let me minimize. Okay, so if we extend this line, and then from here, let's extend this. The point that it intersects this part. So we will see that these two angles are equal. Okay. So okay, now let's consider this part as, for example, x. Okay. Now we have an important thing. And if we consider dA times AX, we know equal to AIC AIB. Okay? It is an important point we work on this because XIB, DIC is cyclic. All of them lies on same circle. So let me write it here and then I paste it in the next page. So we can say IC, X, IB, and D is cyclic. So AX, let's try AX times AD equal to AIC times AIB. Okay, now let's cut it and paste in our new page. So from here, let me move this part here. I say, for example, suppose it is 1. We know AIC, AIB equal to these things. So we can say, okay, because we have AD also here, you can write AD times AE prime because of first equation. So by this one, you can cancel AD from both sides. And then it will be AX equal to AE prime. And that's so much good. AX equal to AE prime. Now we conclude what? We conclude here. Because AX, this part, equal to AE prime, it is isosceles triangle. Okay, and as you can see, this line is what? This line is internal angle bisector. So if I consider, if I connect the E to X, so I know what? I know that AX E prime is isosceles triangle. So, and we know AIB is internal angle bisector of this triangle of AX E prime. So it is also altitude and median. So if I consider this one as, for example, M, we don't have M here. No. So we can say what? We can say that MX equal to ME prime and also it is 90 degree. Okay, so XM equal to ME prime and M is 90 degree angle M. Let's cut also this part. Control X, Control V here. It is this. So this part this. Now we want to do same thing for this side. If we extend AD from D, let's see what we have. Let's select brown. We can say again this angle is A half plus alpha. This angle is also A half plus alpha. So it is angle bisector of that. If we extend AD again to intersect this circle omega 2, for example, in point Y. So because these two angles are equal, you can say that, let's connect. I want to again prove that AY equal to AE prime and it is perpendicular to this also median AI. How we can prove that? This equal to this one. Again, we want to use same thing. I know that AD, if you consider power of point A is outside omega 2. Power of point A with respect to omega 2, A with respect to omega 2 equal to AD times AY. Also, you can say AY, A this. Okay, the product of this part to this equal to this to this. So AD, AY equal to, let me show this. When P is outside, let me show you, for example, in what part we've used. Like here, we said PAPD equal PMPN. This rule, you can say that here. ADAY equal to AIAIA. And now I want to use this. Let's cut this one. And the reason is what? Or you can say power of point, or you can say because D I A and Y is cyclic. Because of this, you can say this if you don't want to write with respect to power. So let's only work on cyclic. Control X, Control V here. So we proved this one. And again, I use first rule. By first rule, I know AI times AIA equal to what? AD by this one. AIAIA, ADAE prime. So if I write it ADAE prime, then again I can cancel it is by first. I can cancel AD from both sides, from first term and third term. So AY equal to AE prime. Now let's consider, because AY equal to AE prime, so again, AD AE prime Y is isosceles, and AI is internal angle bisector of this triangle. So we can conclude, let's consider this one N. N is 90. It is also, the proof is easy. You should prove these two triangles are ANY and ANE prime are congruent. So then we can say N is 90 degree and N is midpoint. Means YN equal to NE prime. Okay, let's cut also this part and paste it here. Now we want to use, let me tell you which lemma, last lemma, not lemma 4. And the application of linearity of powers of the points that we said, okay, if PM equal to QM, then a power of P with respect to omega 1 and so on equal to 0. I want to use this. And the reason is what? Because look, I want to find, we said what? We should prove E equal to E prime. So we should prove power of omega E prime with respect to omega 1 equal to power of E prime with respect to omega 2. For omega 2, if I want to consider power of E prime with respect to omega 2, as you can see, E prime and Y, and their midpoint is N. So if we want to apply lemma 4, this line should be radical axis of this circle, omega 2 and omega 3. So we define omega 3 as B circle, let me tell you, BICIA. And we know that BICIA is cyclic. The reason is what? Because of lemma 5 we proved. Okay, because lemma 5 we know it is cyclic. And the radical axis of BICIA, let's consider omega 3. We've defined it. Omega 3 intersect omega 2 is IIA. Okay, the points, the line, radical axis. And now we know that E prime, so let me copy this part. Let me cut it from here. Let me open new page. Okay, let's consider this part here. With lemma 5, we consider this. And we know it is radical axis. So if we consider omega 3, let's consider these two circles here. It's, for example, omega 2, omega 3. And we know E prime Y, and we know that Y lies on omega 2. So Y lies on omega 2, and Let me, for example, consider, because it's outside the circle, consider this circle is a little smaller than this, and then if we draw radical axis, and then if we show this part, so up to here it will be around 122.40. Okay, so it is y, it is e prime, it is n, it is I, the intersection I. Now, if we apply lemma 4 linearity in powers, the points, we can say what power of y with respect to omega 2 minus power of y with respect to omega 3 plus power of e prime with respect to omega 2 minus power of omega e prime with respect to omega 3. We know it is 0, okay? Now power of omega 2 with respect to y is 0 because y lies on omega 2. We proved this. Let me show you when we proved here. When p lies on circle, power is 0. Now let's consider power of y with respect to omega 3 and power of e prime with respect to omega 2 and power of e prime with respect to omega 3. Let me tell you something. If we draw the figure in exact shape, we said BICIA by lemma 5 is cyclic. Let's go to lemma 5. I want to tell you a property here. By lemma 5 we said it is 90, it is 90. So IA is diameter, okay? And the center is here. So if we consider omega 3, that it is this, IA is diameter. Okay, so if I try to draw exact figure here, let me consider this IA. So our circle will be something, let me draw it with other color. Our circle will be something like, let me show you. Okay. It is something like this. And when we draw, it's still like this. Now we know yn equal to ne prime. And we know it is diameter of omega 3. So if we consider it is, for example, O3, center of omega 3, and if we draw these two lines, we want to calculate power of y to omega 3. It is what? By definition, we said it is y03 squared minus r3 squared. Power of e prime to omega 3 is what? It's e prime o3 squared minus r3 squared. Now, y o3 equal to e prime o3. The reason is what we said that yn equal to ne prime. We proved yn equal to ne prime. And these two triangles are congruent by two sides and an angle between. We can say triangle YO3N is congruent to triangle NO3E prime. So we can say YO3 equal to E prime O3. So because these two things are equal and R3 are equal, these two terms are equal. So we can cancel this and let's say something, because both of them have negative signs, so we can conclude something. We can conclude power of e prime omega 2 equal to 2 times power of e prime to omega 3. Okay? And now we wanted to prove what? We wanted to prove, let's pay attention to sentence, power of e prime to omega 1 equal to power of e prime to omega 2. We can say similarly, power of e prime to omega 1 equal to 2 times power of e prime to omega 3. similarly, and I will tell you why it is similarly. And then by these two things, we prove that power of e prime to omega 2 equal to power of e prime to omega 1, and then we will prove this. Okay, let's see how we can prove these two things are similarly. If we consider, and let me just tell you also something, power of e prime to omega 3, e prime to omega 3 is what? Omega 3 was bi, c, so on. It is e prime c to e prime b. 2 times e prime c to e prime b. Now, let's focus on this word. For this word, we should pay attention to these two circles, omega 1 and In this case, we should consider omega 1 and we should consider omega 4 is circumcircle of. And let me tell you something. Similarly, it's not omega 3. We will find something that it is equal to that. So in first case, that's the reason I say we should check. That is it exactly similarly or not? It is equal to this, but we should prove something, then we prove this. So let's erase this similarly and focus on power of e prime. Omega 4 we consider IB circumcircle of IB, IC, BC. Okay, it is omega 4. And omega 1 intersect omega 4 is what? Is this line. Radical axis is IB, IC. Then here again I want to prove power of e prime to W1 equal omega 1 equal to power of e prime to omega 4. And power of e prime to omega 4. Again it will be e prime c to e prime b. Okay? Okay, let's do the same thing here. We should consider e prime m x and omega 1 and omega 4. Let me cut this part. Control X. Control V here. And we know it is, for example, omega 1. And we draw another one, IBIC, like that. Let's consider in general, for example, we have different size, like something like this. Okay. And then we consider it is IC, IB, it is omega 1, it is omega 4. And why IBICBC cyclic? Because of, I proved in lemma, I think 6, yes. So by lemma 6, it is cyclic. Okay, let's draw the figures. And we know what? We know that if we draw ICIB, E prime and X, M is midpoint of that, and this line is perpendicular bisector of E prime X. So ICIB, let's consider something like this. Okay, we consider it is IB, IC, it is IB, and it is omega 1, it is omega 4, and then we draw radical axis here. Then we consider, for example, Y here. Let's consider, let me consider this point. This is around 143 to 86. Okay, so it will be some point here. And the names were XM E prime. E prime. Now let's see. We want to consider again linearity because we know mx equal to m e prime by lemma 4. We can consider power of e prime to omega 1 minus power of e prime to omega 4 plus power of x to omega 1 minus power of x to omega 4 equal to 0. Again, because x lies on omega 1, it is 0. And then we want to consider e prime like previous case. E prime and x. Can we say that they have same power with respect to omega 4 or not? We should consider omega 4 first. We had in this part. If we consider the angles, here again, like previous one, okay, like previous one that we've said IIB is diameter, here also I want to prove same thing. I say if I draw this, it is internal angle bisector, external angle bisector of C, so it is 90. So IBIC is diameter. So let's now apply this on the figure. We can move a little the green circle. Let me move it. Okay, now it's a little better. Again, I want to prove that y, this part, power of e prime to omega 4 equal to power of x to omega 4. Again, it has same reason. You consider O4, you know power of e prime to omega 4 is what? Is e prime O4 squared minus R4 squared by definition of power. And this one will be XO4 squared minus R4 squared. And XO4 equal to E prime O4 because triangle XO4M congruent to triangle, let me tell you, O4M E prime. Because these two triangles are congruent with what criteria? With two sides, because M is midpoint, two sides and angle between. Also, you can say it is perpendicular bisector midpoint and also perpendicular, so XO4 equal to O4 E prime. And the reason of that is because of two congruent triangles, O4 E prime. And here because of two sides and an angle between. And then we can say, okay, these two things are equal, so power of E prime to omega 1, because these two things are equal, is 2 times power of E prime to omega 4. Okay, now we can say, okay, by this part, power of E prime to omega 1 equal to 2 times from here, power of E prime to omega 4. And power of E prime to omega 4 is what? It passes through BC, IBIC. It is E prime C, E prime B. So we can say it is 2 times E prime C, E prime B. Now we can say they are equal. Okay? So we proved the power of these two things that we wanted to prove are equal. So the sentence of the problem is power equal. So E prime lies on radical axis of omega 1 and omega 2. So E prime lies on DF. So E prime is E. And we proved this problem complete. Okay. So I told you one homework in the beginning of this video. Let me tell you the homework on. Homework number 1. Let me write another homework problem related to, let me tell you, it's for IMO and it's related to X centers. Okay, let me search through the file. It was this, and let me tell you the problem related to that is what. Okay, there are things. You should learn these important ideas. Let me see, the problem is 9-point circle. Problems. Okay, the problem is this. Third problem, also in this problem, it's last problem. Third problem of IMO 2013. Let me paste the problem. Look, there are also another ideas that you should memorize. As I said, 40-50 important formulas in geometry. Also in combinatorics, we have same thing. And X centers, 9-point circles, in internal angle bisectors, when you have in circles, the properties between them. If you want to learn those ideas, in combinatorics also we have important approaches, recursive sequence, you can solve from problems from basic level up to IMO in number theory, we have some important ideas. Also algebra, for example, in function, we have around 12, 15 important ideas. We've used some of them in USAMO, USAJMO. If you want to learn all those ideas that improves your problem solving, as I said before, feel free to send message to my WhatsApp number in the description comments. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. Take care. Be safe. Bye.